Hello and welcome to another episode. I'm pleased to be joined today by Stephen, who is a computer scientist. I know nothing about computer science or even what it is. So, in today's episode, rather than you learning from me, I'm going to be learning along with you. Let's get started. Okay, good morning. Thanks for being here.
Thank you for having me.
My pleasure. So, first thing I figured we would do is just introduce yourself and how did you get into computers?
Yeah, so my name is Steve. I have a master's degree from a pretty good school in the South. I don't want to go into too much detail there, but I got 99% of my PhD in computer science. I got my master's degree in computer science. I got my undergrad degree in computer science. I didn't quite finish my PhD because the real world and real money called me, but I did the academic chops. But how I got started, I think 90% of computer scientists would say the same story, which is they wanted to make video games when they were 10. And someone told them to make video games, you needed to learn how to code. And then when I started that, I was very obsessed with, I'm only going to learn this to the degree that is necessary for me to make all the video games I want to make. But as I learned it more and more, I fell in love with it more and more and stopped wanting to make video games. So that's kind of how I got started.
That's cool. Yeah, I wouldn't have guessed that, I guess, but that does make perfect sense. Did you ever make a video game?
I've made a couple, nothing publishable or nothing that was professional. And I've moonlit for some game companies, but I don't want to talk about who right now.
Oh, that's
but
cool.
yes.
Have you ever used like Unreal Engine or anything like that?
Mm-hmm. Yeah.
I tried to, but I don't understand. There's too many specific steps. It's like, what's an aspect? I don't know what that is.
Yeah.
So that's interesting. All right. So my first big question is, what is a computer?
So I'm going to wax philosophical a lot during this discussion because I think that what's really cool is that computer science is actually not really what most computer scientists do. And most computer scientists in practice are software engineers or teachers. But computer science as a science is not engineering. And that's important to know. And I want to talk about why. So this is going to sound real vague and abstract and philosophical for a lot of this. But here's my answer to your question. What is a computer? A computer is any system which can perform computations. So obviously, really unhelpful. The next question is, well, what's a computation? And this one's kind of cool because this starts to get to the meat and the potatoes. A computation is a process, which is like any defined process or procedure which transforms information into other information. Well, okay, vague, but then what's the next natural question? What is information? And that's the really interesting part here that I think I'm going to try to focus on because I think that's the real meat and potatoes of this question.
Can I interrupt for just a second?
Yeah, absolutely.
So hearing that, there's two things I think of. One, the word computer predates, like the use of the word computer predates what we think of, like digital computers.
Yes.
Because people that would just calculate things for a living on pen and paper, or maybe even punch cards, were called computer. Is a punch card machine technically a computer? I guess it is, isn't it?
Yeah,
but
I would say yes.
Yeah, people that did it completely on pen and paper were called computers, right?
Right.
And the other thing, when you say something that we'll probably get into this later, so just give me like a sneak preview. When you say something that transforms information, me, the biology teacher, the biology major, I think of going from DNA to RNA, transcription translation. So
yes,
that's in this philosophical definition, that is a kind of computation. Would you say?
Absolutely, yes. That's actually in my notes.
Oh, cool.
Already. So we're going to get back to that.
But we'll get back to that eventually.
Yes.
I just wanted to make sure that I brought that up. So continue with wherever you were going.
Yeah. So I want to talk a little bit about information because I think what is information is really important. And it sounds easy, people are just like, oh, information is just like knowledge. Well, yeah, but like from a scientific perspective, how do you formally define knowledge? And I have a good example that can give you the good introduction. So the introduction is, if I flipped a coin and you didn't know what the coin was, heads or tails, then the coin could be in either state in my hand, and you don't know which it is. And so you don't have very much knowledge there, right? But then once I show you the coin, you now know that it is not in one state. It is in another state.
Okay.
And
but
the
answer was always there.
That's knowledge. Yeah, it was.
Yeah.
But now the knowledge exists in your brain.
We transformed information into knowledge.
Yeah. Like, I'm just saying the concept scientifically of what information is, a good example is you go from uncertainty to certainty. You now know something about the system that you didn't know before. A yes or no question. And it's typically recorded. It's basically information is the state of a system in one specific configuration as opposed to another state. This is really close, actually. So like when we talk about knowledge in computers, we're really talking about, in computer science, like a sequence of yes or no questions. And I think a good reason why we do that, and that's what binary is like, if I wanted to know what your age is, for example, let's play a really quick guessing game. So I'm going to figure out your age using a sequence of yes or no questions. Okay?
Okay.
So, are you older than 25?
Yes.
Are you older than 50?
No.
Are you older than 40?
No.
Are you older than 35?
No.
Are you older than 30?
Yes.
Are you older than 32?
No.
Are you 32?
Yes. I
so
looked up and that probably gave it away.
I asked 10 yes or no questions, and those 10 yes or no questions allowed me to resolve which specific number of the possible numbers from 18 to 70 is exactly corresponding to the data. And so you can use yes or no questions to actually store any kind of unknown information or any kind of discovered information. A single yes or no question can always reduces the number of possible unknowns of a question or a system in half. And so just by induction, an infinite or a certain sequence of yes or no questions can always distinguish down to the actual information you're looking for.
That's
and
cool.
So information can always be represented as a series of yes or no questions. Any knowledge. And that's why computers work on binary.
Yeah, see, that sounds really inefficient. But a computer can do millions of calculations per second. Mm-hmm. So, what are those called? Well, those are like flops, aren't something like that?
Flops are floating point operations per second. But this is less about what a computer can do and how a computer could do it. This is actually just more about what is, like, for example, when we talk about force, we have newtons. Mm-hmm. When we talk about electric charge, we have, columns, right? Yeah. When we have pressure, it's pascals. If we're going to talk about information as a science, we have to come up with a standard unit of information.
I never thought of that.
And that's what I just did. It turns out that every piece of information that can be known or described or any state of anything has a certain specificity to it. And the specificity can be measured in the number of yes or no questions that you need to answer in order to fully specify the knowledge that you're describing. And so the sort of standard SI unit of information, if there was one, would be the bit or binary digit, because it's yes or no.
I would have never thought of that, but that actually makes good sense.
Yeah. To know something means to know what it is in terms of what it's not, and bits allow us to do that.
Interesting. That's cool.
Yeah, yeah. So I guess to finally to go back to what is a computer?
Right.
A computer is any system which can implement a computation. A computation is any process that transforms information into other information. Information is just any knowledge of anything that is well defined and well specified and written down. And so it's kind of just like a system that transforms knowledge into other states, or transforms defined states of existence into other knowledge and other defined states of existence. That's a computer.
Do you have any idea how old that word actually is?
Computer?
Or
no, I don't.
Or did we just
probably old?
Yeah, we probably talked about what you're describing in different terms thousands of years ago. We just didn't use the term computation or whatever, I guess.
Yeah, well, I know that the word algorithm is actually very similar to the word computation in terms of definition. An algorithm is an Arabic word that goes back very far. A lot of people get hung up on, if we're talking about social media, the algorithm or using algorithms. And there was a famous court case that I thought was really funny where someone was like, or like senators are often like, oh, well, how can we trust these algorithms? Like it's some magic word. But the truth is the word algorithm just means procedure. It's just Arabic for procedure. That's all it means. It's a defined procedure. So a recipe to make cookies, that's an algorithm.
Oh, yeah. Yeah, I mean, the algorithm, it's just trying to make predictions. I mean, that's
right.
All it does. It is creepy in some ways. I don't know if you've read Homo Deus or 21 Lessons for the 21st Century by Yuval Noah Harari, but he talks about algorithms in ways that are actually kind of creepy. And it's not really, the book isn't meant to like scare us, it's just like to make us aware so that we don't end up accidentally doing something that isn't good for us. Because technology has the capacity to do either.
That's totally true, and you're right about that. And I think we're going to talk about that later too. But I want to point out, I want to clarify what I mean a little bit. What I'm actually trying to say is that a lot of people use algorithm in the way that you just used it to specifically refer to like machine learning algorithms or AI algorithms, things that we encounter in the day-to-day of like social media and these things that are like very modern. But an algorithm is actually much more generic than that. It's just literally any procedure to do anything. So like when you add numbers with long addition grade school, that's an algorithm. When you do, long division, that's an algorithm. When you load your laundry machine, that's an algorithm.
So it's kind of like when people say like chemicals, there's chemicals everywhere. It's like, yeah, water is a chemical.
Correct. Yeah, exactly.
They're not using the word very well. So
right.
Does that have we answered the question? What is
I think so.
Computer to your satisfaction?
Yeah.
All right.
Yeah,
so
I think so.
Now that we know that, and that it answered it to my satisfaction as well. So, with that being said, then what is computer science?
So, what I would say is that computer science is sort of the study of the scientific method itself in a formalized way. Another way you could talk about it is you could talk about it as like a type of applied philosophy, because it's like a mathematical formalism for philosophy. And it's almost like mechanical linguistics. It's a lot of things. And all of these are kind of swirling around this nexus of, if we're going to study the procedure that can be used to transform one type of knowledge into another type of knowledge, and we're going to learn things about how those procedures work, we're going to learn things about what their limitations are, we're going to learn things about the creation of knowledge, the manipulation of knowledge, we're going to learn if there are any limits to things which can be known and cannot be known. Because essentially computer science is discussing the very abstract, how do we build procedures and systems to process knowledge and make it into new knowledge?
So it's like we're trying to get better at getting better at knowing information.
Exactly. And also, what can we do with the information we have? What new information can we learn? It's very interesting to say okay, well, you know, if I know that this is true and I know that this is true, then by induction I can know that this other thing is true. Absolutely. But that right there is a very basic algorithm. But the question is, okay, if I have these measurements of a sound wave, what can I do to transform that sound wave into music notes or music chords, represent new information in a different way? And how do I actually do that, and why? That's why computer science shows up as a subfield of every modern science, to be honest with you. Like I had to take a bunch of science classes that were not a part of my major because it was expected that I would end up talking to physicists to help them with their problems to make their inferences. I would be talking to biologists to help them make their inferences. And this is also why every physicist learns to code, and why every, like, you know, mathematician is learning to code. It's because it's like, at some point you have to use the tools that have been developed by computation to derive new knowledge effectively.
Okay, yeah, that makes sense. So hearing you describe what computer science is, to me it sounds like engineering.
Kind of, but remember, we're not really necessarily the type of computer science I'm talking about. We're not actually going to be building the computers. Like in practice, like I said, a lot of people do that, where a lot of practical computer scientists are engineers because they're actually doing it. But computer science as an academic science is actually studying, like, what is knowledge itself as a science? What's the knowledge's limitations? You can't always design a program for something, and why not? Or how do you design a procedure for something that no one knows how to do? What inferences can be developed about how you might go about discovering the phase angle of something that can't be measured correctly, et cetera, et cetera. There's a good example of this is that I just thought of, so it's not in my notes, I just thought of this, is there was a huge advancement in computer science recently for MRI machines, where it was previously believed that you needed to measure every single possible data point of, like, someone's, you know, whatever bone or whatever you were trying to measure using the MRI machine. So MRI machines would take a very long time because they had to linearly measure every data point. And there was a computer scientist who discovered something called compressive sensing, which actually proves that the information theoretical bounds for MRI machines and other types of sampling is significantly lower than we actually previously thought. And that created an algorithm which could be used to get the same resolution of MRI data from only 5 or 6 measurements. And that's actually saved people's lives. But there was no engineering involved in that discovery. It was a pure math discovery that only looked at the mathematical properties of information and sampling itself.
Got it. Yeah, that reminds me of the discovery of Neptune. A mathematician looking at the orbit of Uranus was like, so its orbit, the shape of its orbit or its ellipse or whatever, it wasn't what it should be given no interference from other planets. So people hypothesized there must be a massive planet out there as well. So we're talking, this is Uranus this is Uranus, that's Neptune. So they hypothesized a planet out there, and he sent the data to an astronomer. I think it was, I can't remember. And he found it the night he was given the information of where to look. He actually found it. So, like, the pure applied stuff versus the real world application. That's cool.
Yeah.
All right. So next, what's the difference between an analog and a digital computer? Like, intuitively to me, the only difference I can really think of is one doesn't run on electricity, right? So I would assume that you can't really have a digital computer that doesn't run on electricity. And a digital computer will have moving parts, but far fewer than an analog one. That's what I think anyways. But what the actual difference is, I don't really know.
That's also, yeah, so that's not quite correct, unfortunately.
Figures.
But You can have an analog electricity computer, and you can have a non-electrical digital computer. Basically, the way to think of it is to go back to that definition of information that I talked about, where information is like a defined state of a system, right? So information itself can be analog or digital. For example, assuming time is continuous, we're not going to get into quantum mechanics here. Technically, is your age actually exactly 32? And the answer is no,
no,
because time is like a continuous variable. What I did with my yes or no questions is I sampled a continuous variable to some resolution to turn it into a series of yes or no questions, right? But I could have gotten into more detail. I could have said, were you born with additional bits? I could have said, are you born in January? Are you born in, June, whatever? Were you born after 10 p.m.? That's because time is a continuous piece of information. It's not like discrete states. And if I want to convert it into discrete states, then I have to like choose a sampling resolution and answer as many yes or no questions as I can. So information that exists in the universe can be continuous, and then we sometimes digitize it when we work with it by turning it into a discrete description. Like as an example of an analog system that's electrical, the amount of volts that's on a speaker wire, for example, that would be an electrical analog continuous signal, because it doesn't just toggle between a certain number of states. It doesn't just toggle between 0 and 1 on or off. If you look at the volts in a speaker wire, or like the waves of AM radio, for example, these are things that use continuous variables. The amount of water in a jar is a continuous variable. The magnetism of a segment of plastic tape with iron particles on it, like an old tape deck, or like an old VHS tape, that's an analog measurement, because the number of particles is technically like a finite integer, but we model it continuously. Whereas digital information is discrete information. It's not continuous. There's a finite number of possibilities of what the information could be, and it's one of those possibilities. So, if I said, what year were you born? That's a digital measurement, because the number of years is only a certain number of years. But if I exactly, in some kind of universal sense, how much time has passed since you were born, that's a continuous variable. So analog computers process continuous variables into other continuous variables, and digital computers process discrete variables or into other discrete variables. So like an analog computer that uses electricity really would be, in my opinion, like an old analog radio, because it's amplifying certain things, it's tuning certain things, it's isolating the analog signal from the other analog signals and extracting a certain waveform. Those are analog measurements. You can actually also build computers out of like pressure, like plumbing in your house, sort of, but more complicated. Yeah. And quantum computers themselves are actually kind of a type of analog computer. There's some asterisks there. Computer scientists in the comments can call me out. Versus, so a digital computer, what you're thinking of is a digital electronic computer.
Right.
So it's both digital and discrete, on-off pulses, processing on-off data, and it's using electricity to do that. But you could have a digital, like, for example, if you had gears, right? A set of gears, there's only a certain finite number of configurations that the gears could be in. That would be a digital computer. It just would.
I grabbed this. Is this watch? Is this digital or analog or?
I would say it's analog, but I'm not a watchmaker, so I don't
Yeah,
know.
that's what I would have
Uh,
guessed. I was like, is this an
maybe if
example of, because it's constantly in motion and then it constantly produces information about what time it is. And
right.
because I wanted to get an example of continuous to continuous data or information.
A
Or
pulley would be a good one.
a what?
Pulley system. A pulley system.
Oh, okay. Interesting.
Right? Continuous to continuous information. There was an early an early electrical analog computer that was used, I think, in the 30s and 40s during the war, that was able to calculate bomb trajectories by creating
Oh,
the
the Norden bomb
voltages.
site.
It was able to create voltages that were, and then the voltage wiring created and simulated the analog trajectory calculations. It wasn't digital. It was only using it was basically like calculating a trajectory using a pulley system.
Is that the Norden bomb site? I read an entire book about
Maybe. I don't remember. I just remember, I'm vaguely coming to mind of it. I don't know if that's the same one or not. But yeah, the reason why I say I don't know, though, about your watch is because I'm not a watchmaker, and I think
Right.
there's gears in there.
Yeah.
And then someone could say, well, Steve, you just said gears means that there's only a finite number of states.
Mm-hmm.
So, and I'd be like, well, okay, fine. So
Well,
I would say a pendulum is more analog, but maybe gears are more discrete or more digital.
It's like a grandfather clock.
Mm-hmm.
Interesting. Okay. Is there anything else about analog digital computers?
No.
That
I think that answers the question, in my opinion.
Okay. All right. So now,
if you have any questions about it,
I don't think I'm smart enough to. Well, I got some other questions later on that are related to it, but at this moment, I don't think I know enough to even come up with a new question. But
yeah.
So now we get into some of the deeper questions. Is the brain a computer?
You tell me based on what I said. Pop quiz for the class.
I feel like what you said earlier when I asked about DNA and RNA, I feel like that's a kind of computation. Is the brain itself a discrete computer? I feel like it's hundreds of billions of them, and then but can something be a computer and be that? Or is it more like the cells are the processors, and the brain is the computer?
So that gets to some questions. I would say that when you model the question of whether the brain is a computer, we're not going to treat the ribosomes as part of the computer's operation, because the ribosomes are not really. They're doing something specific that's not directly related. They make the brain rebuild itself, but they are not the functionality of the brain. As far as I'm aware, you're more of a biologist than me, but your ribosomes are not what makes it so you can think. I thought it was the configuration of your neurons. Is that right?
Well, obviously the brain couldn't do what it does without them. But
yes.
What the brain does is the result of neural pathways.
Correct.
We could say in the brain. So yeah, what you're saying makes sense. Yeah.
Yeah. So I guess my answer would be ribosomes. Our ribosomes are in fact definitely computers, but they're not the computer that you're asking me about. What you're asking me about is, does the configuration of neural pathways that count as a computer? And I would say trivially yes. And I would say because we process information, there's a defined state of information in our brains that gets transformed into other information. We receive input from the outside world in terms of things that we see or don't see, and then we process that into inferences. I'm doing it right now. I'm responding to your words, doing something with them, and then spitting more information out. So there is the translational property that I was describing as the definition of a computer. Yes. Is it a digital computer? I would say no. I would say it's closer to an analog computer. But I don't know that much about how brains work, and that's something I think neuroscience is still struggling with.
My gut tells me it's analog, I guess.
I think it's kind of an analog computer too.
Yeah.
But
this reminds me, I think there's this podcast I watched once with Roger Penrose, and somebody asked him, I can't remember, they either asked him, is the brain a computer or is the universe a computer? And he gave like an hour-long answer that didn't make any sense to me. I don't remember what any of it was, but that just kind of reminded me.
I would say the brain is an analog computer made out of meat.
Yeah, sure. So I like when you're talking about like what is it that the ribosomes or the cellular machinery actually does, it's not the same as what the brain does. And so like
Correct.
I wrote down, tell me if you think this makes any sense. The parts of the cells, like if we're going to draw an analogy to like a computer sitting here in front of me, it's like the cells or the parts of the cells are kind of like the electricity, and the brain is the computer in a way.
That's kind of what I was saying. Yeah, I think that's accurate.
That makes sense.
And the cells themselves also need to be functional. And to do that, they need ribosomes, which are smaller computers. And if they didn't, then the cells would die. But I don't think the ribosomes are themselves the computer you're asking me about. Yeah. It's like wheels within wheels.
So, well, when I was talking about, converting DNA to RNA, that a ribosome isn't used for that. A ribosome is used to turn RNA into proteins. So transcription is the process of going from DNA to RNA. Now that's taking information and turning it into it's taking, creationists use this talking point. They talk about DNA as a literal code. You know what? I want to know what you think.
Is. To be fair.
Sure. So I kind of think like, well, it's a molecule. I mean, it contains, if we can call that a code, then I feel like it contains information to make RNA. Now, if we're going to call that like a literal code, okay, but we would also say like an individual atom has that, because the configuration of valence electrons in an atom is what determines what its chemical properties are. So then, is an individual atom, does it contain a code?
Yes, but I think you're hitting on exactly the point, which is that, just like you said, I forget what was the exact analogy used a few minutes ago of like
the ribosomes of electricity.
Well, no. Even more earlier than that, you were like, it's technically true that like water is a chemical.
Oh, right, yeah.
Like, yes, like DNA is a code and DNA is information, but also the valence electrons are information. Also, whether or not, my shirt is blue is information. That is not it actually is ironic. It takes more information to express something that's totally mixed up and random than it does to express something that's ordered. Because if you think about it, like, if I just had 500 coins, then the only way to in random order, and I flip them all, the only way to express the information would be to read out all 500 bits. There's no way to make that any smaller. But if I had 500 coins and the first 250 were heads and the second 250 were tails, all I have to say is 500 coins, half heads, half tails. And that's less information. So random, it doesn't necessarily mean anything about a creator or critical to like, oh my gosh, there's so much information in DNA, because of course there would be. That doesn't mean anything, So it is a code, and they're right. It just doesn't show what they're trying to show.
Yeah, it's just if that's true, then it's also true that almost everything is a code. So it's like, well, right. Your point about DNA isn't super special. So I remember there's this Veritasium video. I don't know if you watch his stuff, but it's actually one of his old videos about what is randomness. And from what I remember, for something to be considered truly random, it cannot be expressed in simpler terms than something like the number of variables or parts that it's made of.
Yep.
Okay.
Exactly.
Because like for what you were talking about, like it's kind of like efficiency. So like this video that's being recorded, my computer is the stuff in the background doesn't change, so it doesn't necessarily re-render a lot of that stuff. It just kind of leaves it alone. This is what compressed video is, right? Yeah, so
That's right.
it takes less computing power. My face and my body is always changing, but like that guitar right, I'm not going to touch it. That guitar right there isn't changing, so it's not necessarily producing new data about it constantly.
That's right.
Whereas it has
and
to.
analyzing what entropy or what information is relevant to the human visual system versus not relevant for the human visual system when looking at a video stream, that's something that a computer scientist did. And that's why you can compress a video stream down from the raw measurements, which is way more information than you need to represent it, into the optimum representation. However, if you were just showing a video stream of random noise, it would be incompressible, just like you said. And you can actually even try that. You can show static and try to upload it to YouTube, and YouTube will get really mad at you.
Yes, this video is huge. What are you doing?
Yeah.
That's
right.
Yeah,
and it's huge because of that, because the amount of information content is more.
That makes perfect sense. Yeah, like when I upload videos on my computer, some of them there's just a still screen, and so the file's really small, even if it's like 30 minutes or whatever. And that makes because there isn't any video information there. I mean, it technically is a video, but it's just the same thing over and over again. Getting back to, so if going from DNA to RNA is transforming information, then couldn't we call the cell a computer because it does that?
Probably, yeah. I actually used ribosomes on purpose, and you're right that I know that the DNA to RNA is not what a ribosome does. The ribosome creates proteins from reading the RNA. Am I right about that?
Yeah.
So I wrote ribosome in my notes only because the DNA to RNA transcription, even though I would agree with you that it's a computer, I felt like someone could come in and say, well, it's not transforming it, it's just copying it, because the DNA to RNA is a copy from the unzipping.
Not quite. I would say DNA replication sort of is, but
okay.
RNA has it has a fundamentally different structure, and there's a different nucleotide in there. RNA has uracil, and there's no thymine in it.
Mm-hmm.
But it's
but that's a subjective thing. But
yeah.
But then turning the ribosome functioning to turn the RNA into completely unique proteins by doing some interpretation. You can watch a video of it and it really looks cool as hell, like a little machine.
Yes.
That seemed just to be more obvious to me as a really obvious example of transformative data. But I think they both count. I would agree with your assertion that they both count as computers.
Okay. So since we're talking about computers, was the Antikythera mechanism the first computer? I've heard that it was an analog computer. So basically, do you agree with that? Okay.
Yes, I do. However, I'm gonna language lawyer your question. Uh-oh. I think the first computers are the self-replicating RNA at the beginning of life on Earth.
Sure. So was the Antikythera mechanism the first computer to be invented?
I would say probably. There is. I did some research on this for this interview because I thought it would be cool. And I wanted to make sure I was telling the truth. So the Antikythera mechanism is an analog computer that was invented by people. I don't know if it's the first, and the reason why is that it was actually one of a bunch of things that were like kind of common in that time period that had been built for like a couple hundred years, according to the records that I found. So it may be the first that we have an example of, but the like documents we found nearby it says like, yeah, this is like version 5 of something that like a lot of people have been building for 80 years. Yeah. So presumably there were others.
Yeah, it's the earliest one we know of.
Yeah.
But yeah, the idea that it was literally one of one It's like, well, I mean, probably not. If
Yeah.
like the amount of, I just can't imagine how somebody who they couldn't stamp metal, they couldn't forge metal at that time.
Hmm.
Well, I think, well, maybe you could forge some metals, but not gears. Like the idea that somebody figured out, I don't remember how many gears it has, but I'm sure it's an absurd amount. Somebody figured out, okay, the gear has to be this exact diameter. I have to shave this exact number of teeth into it. Um, and you're gonna have hundreds of gear interactions. And it's like, yeah, so if I do all of those, then it'll predict when the next lunar eclipse is, up to like I think it could predict things up to like 30 years in the future, I think.
Hmm.
Something like that. And it's like, how I can't wrap my head around how somebody could have figured out that it's just so complicated. It's like a three body problem, you know. um
So I
it's
know
just
what
like,
question you're going to
it's
ask,
so
and I
crazy.
want to answer it because I think you're going to like where this is tying back to what I originally said. Um, I think what's cool is you're touching on the essence of what I would call what computer science is. Because, like I said, computer science is the study of the process on how to convert information into other information. And so, if you think about it kind of backwards of how you might go about building something like that, we'll call him first computer scientist building this mechanism. He would think the information that I know is that this gear has to, like, that the output needs to look like this. How can I make, what do I need to know in order to make the output look like that? What do I need to know that? What do I need to know that?
Yeah, yeah.
What do I need to know that? And by working backwards and breaking down exactly what pieces of information can be transformed into other information at each stage of the problem, you then create an incredibly long and complicated pipeline of transformations. But that's essentially what every programmer or every computer scientist is doing in every case. They are analyzing the knowledge. And knowing how to do that as like a meta skill, because there's actually things computer scientists have determined of like, oh, well, not just solving a particular problem, but here is an algorithm to create algorithms to solve problems. So
Yeah.
you can actually deterministically and mechanically sit down and decide on how to build these things. And that's something that is like that study of how to solve problems and how to go from information to information to information. That's kind of what I would call the field of computer science. So maybe the guy who made the Antikythera mechanism was the first computer
Was the first? Yeah, I
scientist.
was just thinking that. I was like, wow, that's really interesting. Um, is this isn't one of my questions, but like, if we just take like the different like fields of math or whatever, would from what I understand, calculus is the mathematics of, it's like the study of change,
Hmm.
something like that. So is that like is calculus like the most essential, like, kind of math for computer science, or do you really just need algebra and you don't need much more?
No. So the problem is calculus is very continuous, and
Oh,
computer
okay.
science is in practice very digital,
Oh,
right?
okay.
Because human brains, despite the existence of analog computers, are not good at it. I'm going to be honest with you. Like when you sit down and you add and multiply numbers, you don't like visualize two circles spinning on a gear thread, like or on like two pulleys, even though that would be a system that could multiply numbers. Instead, you write down the numbers as digits and up to some accuracy and also digits, digital. Now you get it.
Yeah.
Um, you write down the numbers up to some accuracy, and then you perform the algorithm on the discrete number of digits, and that's how you multiply. Human brains are ultimately not super great at analog computation, and we're just don't work with it very well. And so most computer science is digital computation. It's discrete symbols, it's discrete steps, it's toggles on off. So the key, and it's also linguistics and ideas and abstractions. So I would say the key parts of math that are important are like logic, set theory, integers, and also linguistics. So like logic, set theory, integers, linguistics, that kind of thing.
Right. Wasn't
calculus is important though. I love calculus. I'm a very calculusy. For computer scientists, I'm one of the more calculusy ones. So, okay, but cool. I would say it's not really what the focus was for my field.
Yeah. It's like when you're talking about brains, like brains can do these kinds of computations, but they're really bad at it. And it just kind of reminds me of like the brains are so much better than computers at some things. Like we can't do math. we're so bad at it compared to a computer, because a computer can multiply two 50-digit numbers in no time at all. But a computer, if you showed a picture and be like, pick out the cat, the computer until recently can't do it at all. So
I want to touch on that really quick because I love that point and I want to call it out. Something so let's put on our computer science hats a little bit. One of the things that is kind of cool about deep learning is that deep learning, just like ChatGPT and like the image and picture generators that you were talking about, is the way it was invented was basically attempts at AI by using discrete and digital logic were essentially failing throughout up until the 90s. And so we kind of realized, well, we know that computers exist that can do things like write poetry and recognize because our brains can do it. If our brains can do it, computers can be built to do it. Right. Therefore, why can't we figure out how to do it? And so what the fundamental kind of intuition behind deep learning is what if we kind of did more like neuron type computers, more analog-ish computers, more like networks of deeply connected meshes of reacting, activating cell structures? Would that create something that is better at doing things that our brains can do? Kind of inspired from biological brains in a way, except we just simulate the analog computations on a digital computer because we have more of them lying around. So we're simulating the analog computations of neural nets and neural biology on digital computers, but the actual computer that's doing that processing is much closer to a brain than a calculator. And the cool thing is that what you would predict if that theory is true that you just talked about brains being good at certain things and not others, is that ChatGPT would be good at feelings and bad at arithmetic. And that's actually what we see in practice. ChatGPT cannot multiply two 50-digit numbers. If you try it, it gets it wrong a lot. Or like if you tell it to do some complicated binary calculation, it has a really hard time. But if you tell it to write a poem about how a sunset might make you feel, it's great at that.
That's really fascinating. I knew that, but I would have never thought about it in that way. That's really interesting. That's cool. Huh. So it's like, it's become the thing that makes ChatGPT so like creepy and powerful. It's like, oh, a computer that can do this. It's actually a trade-off. It's like, well, yeah, but it's not good at the other thing. It's like if ChatGPT tried to take over the world, it would fail because it can't do the math or something like that.
Potentially, yeah.
That's really
in a way, ChatGPT is like a gigantic brain that's been forced to read books for 10,000 years.
Yeah, basically, yeah.
And so,
I like that.
If you had a giant brain that was forced to read books for 10,000 years, and you said, okay, now calculate the exact, frequency of waves necessary to crack the nuclear codes or whatever, it still wouldn't be able to do that.
That's funny. Yeah, I asked ChatGPT. I have a pool. It's like it's not an inflatable pool, but it's like an above ground one. and it's got like 1,000 gallons of water in it. And I live in the Central Valley of California. It's really hot, and so the pool, the water's just warm. I was like, oh, that's kind of like, it doesn't exactly defeat the point. But I was wondering, I was like, I could calculate this, but I'm lazy because I know how to do specific heat. I was like, how much ice would I have to add to the pool to cool it down by 10 degrees? And so I asked ChatGPT, and it told me I would need 285,000 kilograms of ice. I was like, that's 10 times more than the mass of the water in the pool. It's more than 10 times, I'm pretty sure. And it gave me the calculation, and I just said to it, I said what I just said, and it goes, apologies, and basically the answer it gave was 1,000 times too big. So it figured out what it did wrong. It's like, it's actually 285 kilograms, not 285,000. But
right.
So it learns from its mistakes, but it's very human in a way. That's funny. Okay. Next thing is this kind of a long-winded questions. Who are the most important figures in computer science? So, like, to me, the only names that really come to mind for me are Alan Turing and John von Neumann. And, like, for people that don't know who John von Neumann is, I would say next to Albert Einstein, he's the greatest scientist of the 20th century. And I would say it's not even remotely close either. Because if you go to his... he never won a Nobel Prize, but if you just go to his Wikipedia page, right under their... Like, it gives their short bio... under their picture, when they were born, blah blah blah, and then it says known for, and there's a list of things. John von Neumann, his known for thing is, there's like 123 things that he's known for, and they're all in the fields of mathematics and science and computer science probably, and all this stuff. And it's like, he's the most prolific scientist and mathematician. And it's insane. So I just wanted to add that because nobody knows who John von Neumann was. So with all that said, who would you say are like the most important figures, maybe like top 3, and why they were so important?
Yeah, so I want to talk about Turing separately because you said not him. And von Neumann is cool, but even though he's amazing for every reason you said, not the person who would come to my mind.
Okay.
But the 3, I have 4 written here.
Oh, that's fine. Yeah.
One is Gödel. I always mispronounce his name because
it's pronounced Gödel. Yeah.
Gödel. Yes.
Gödel, yeah.
He is, in my mind, one of the people who was incredibly important, because in doing the incompleteness theorem, he kind of showed the outline for how formal systems and linguistics are inherently tied together in a way that he invented something called Gödel numbering, which it was the precursor to showing that like all math and all formal systems can be represented as integers, and also that means things about the properties of knowledge itself. And that was something I think that was a huge, like almost like computer science thing. There's a lot of formal proofs in computer science, like the halting problem and Rice's theorem and all these other things, which are really important towards foundational, like computer science theories that all derive from the incompleteness theorem proof rewritten in different ways. So I think that's very cool. The next guy who's important is Claude Shannon, because he kind of formalized and invented the definition of information that is standard today, and like discovered the basics of like I talked about earlier, the metric standard measurement of information and how that can be used to represent anything, and knowledge and like transformations with it. That's all what Shannon did. He created all of that. And that's huge. And then there's Church. Church was Turing's mentor, And basically, together with Turing, they discovered something called the Church-Turing thesis, which is awesome, and I want to talk about in a second. But basically, a lot of what Church did was establish how the mathematical properties of algorithms and the mathematical properties of computers and like information theory itself could be analyzed, like actually formally analyzed. And then the last one is a much later guy named Donald Knuth. He is well known for just writing a ton of books about set theory and algorithms and practical computer science stuff. But what he's known for that he popularized, he didn't invent it, but he really he named it and did a lot with it and did a lot of the early papers with it, is something called algorithmic analysis, which Church and Turing were very interested in. With an infinite amount of time and an infinite amount of resources, can this be computed at all? So they weren't necessarily worried with whether it was practical to derive a certain piece of knowledge or discover a certain fact. They just wanted to know, kind of in the sense that you were talking about earlier, of, can this information be fully derived from this other information, deterministically in an infinite amount of time? But that's not practical because none of us live forever. You want your phone to be able to produce the answer in a finite amount of time, ideally, and preferably before the heat death of the universe. And so the analysis of algorithms stuff that Knuth really kind of spread out and spread around and wrote a lot of good papers on allows computer scientists to go beyond what Church decided and say, well, this is possible in theory, versus saying this is possible not only in theory, but within, 10 minutes or within 10 years or in a certain number of steps, and be able to analyze that. And that was huge for computer science, because knowing that you can compute something in the heat death of the universe is not valuable ultimately towards practical problems.
Right. Yeah.
So and Turing is great though. Turing is fantastic.
Yeah. And we're gonna talk about him more later, you said?
Yes.
Okay.
I kind of wanted to. I can launch into him now. Actually, that's the next step. But yeah, what's the next thing that you want to kind of ask about?
So yeah, the Turing stuff will come up next. So, I was thinking, Einstein didn't invent the laser, but but nobody knew that a laser even could exist until his research came out. So what you were talking about earlier kind of made me think about when you're, I don't know if you've ever tried, when you try to solve puzzles or do escape rooms or something, and you just get stuck, or weird word problems, like the game Mad Gab.
Mm-hmm.
If you ever play, it's like you're stuck. You're like, I can only think that it's probably this thing, and it's impossible to think outside the box. So the answer becomes so obvious once you figure out the trick to it or whatever. And so what you were describing earlier kind of made me think about that. It's well, these systems actually become incredibly efficient and they work really well once we realize, no, think about it completely differently. And
that's right.
And then we're off to the races. But anyways, so
that's right.
Einstein didn't invent the laser, but his work told us that it was possible for them to exist, and then they were invented in the 50s, I think. So do you think that the type of computers we have today, would have been invented without Turing? Not eventually somebody would have done it, but do you think we would be we'd have the computers of the 50s or 60s today if it weren't for Turing? That's more of what I mean, I think.
Yes, with an asterisk. I want to answer the question. I want to bump and say something really quick as an interjection, though. Mm-hmm. I love the puzzle example that you gave so much. It's great. And what I would say is that puzzles of that nature are fundamentally related to computer science, right? Because in a way, you are trying to solve an information problem, and you're trying to think about what is the procedure that I can use to take the information I have about the puzzle so far and turn it into new information about what the solution is. Like, that's all computer sciencey things. So I just wanted to say that, and I love it. But let's answer the question. I'm going to go into a little bit more detail right here about what Turing actually did, because a lot of people just say he invented the computer, and that's not really true.
Yeah.
But the answer to the question is yes, but we wouldn't have understood them so deeply. We would have invented them and not really known how or why they worked.
Oh,
if that makes sense. So here's kind of really what Turing did that's important. Turing and Church together were really interested because, remember, like I said before, I said a computer is anything which can perform computations. A computation is a well-defined process to transform information into other information. And so we came up already with tons of examples of what that might look like. We came up with, like, okay, the ribosome thing, we have the RNA thing. We talked about human brains. We talked about digital computers. We talked about gears, clocks, watches. What do all of those things have in common, like mathematically? What is the Platonic ideal of a computer? What properties does a thing, a physical system, have to hold that make it a computer? Mathematically, what is that Platonic ideal? What is the fundamental properties that everything would have that would make it a computer? And if it doesn't have these properties, it's not a computer. How do we determine that? What is a computer and what isn't? And so Turing and Church were trying to answer that question. And so to do that, they were trying to create abstract computers, not real computers at all, purely abstract computers constructed only of ideas and set theory that would essentially have the minimum properties necessary to be a computer and would share those and then everything that was a computer, you could say, had those properties. That's basically what they were going for. They were like, what is the Platonic definition of a computer? And so they found it, if that makes sense. And that's the exciting part. So it turns out that the way they started is they basically said, well, I know of a computer, my brain, equipped with a pencil and paper to store things. And so when I do like arithmetic, I like read and write symbols on paper. I like take the 4, carry the 1, read the next one from the next column, move to the left, put something in, move to the left, etc. So I know I can do that. So that is obviously a computer. And then they kind of said, what about that? Just the abstraction of a pencil and paper and some kind of procedure is fundamental to computing. And they basically determined, and that's what a Turing machine is. You've probably heard that before. It's an abstract computer that is just an infinite amount of tape in either direction. The tape can store a 0 or a 1 on the tape, so it has memory to store state. So computers have to be able to store state somehow. And then it also has a function where it reads from the tape, does something with that knowledge, and changes state somehow in itself, and then in response writes something to the tape, and then either goes left or right. And the fundamental feature there of a series of steps of a program of what to do and when, a tape to store the ephemeral information temporarily, and the ability to select what information you're operating on, it turns out that's the fundamental, that is all you need to build a computer. And so they started thinking, well, if that's true, is it possible to create a Turing machine which can read a description of another Turing machine? Because I could, in designing Turing machines as a concept, he was writing it down on paper. And so by definition, the design of a specific Turing machine to do some function. You can imagine writing out a Turing machine, like drawing the steps that it would take at each point in the tape, and that would be good at like adding two numbers, for example. You could say, okay, well, the numbers are written down on the tape, and then you read the first digit, you do this with it, you read the second digit, you do this with it, you read the third digit, you do this with it, and then you output it, blah, blah, blah. That would be a Turing machine to add two numbers. Now that he can know how to construct Turing machines, he knew how to write down Turing machines. And so the question became, is there such a thing as a simple Turing machine which can read a description of another Turing machine off of the tape and then do what that Turing machine did instead? So the first emulator, if you think of it like that. So is it possible to build an emulator that can emulate other Turing machines? And it turns out the answer is yes. So, and that's the Church-Turing thesis.
So me hearing that, I'm thinking that sounds really inefficient. So why would a computer want to simulate? Oh, okay. So I'm not wrong about that. So like, then why would a computer want to simulate what another computer can do?
Because before this is called universal computing. Before universal computing, if you wanted a computer to add two numbers, you had to physically build the computer to add two numbers. And then the computer could never do anything else other than add two numbers.
Okay. Yeah, like Enigma, all it could do was like algebra. Like that was it. It couldn't do anything else.
Yes.
Okay.
So, because remember, a computer is a system that can process information according to a set of steps. Mm-hmm. But if you have a computer where what it can do is process the information describing another computer and then run that computer's steps, then you build one physical computer that does that one function, the emulator function.
Yeah.
But now your emulator computer can do anything that any computer that you can write can describe, can do. And that's where software versus hardware comes into play. Because now that you have a universal Turing machine implemented in whatever system you want to implement it in, you could build a universal Turing machine out of electricity. You can build a universal Turing machine out of gears. You could build a universal Turing machine out of fluid pumping through wires. Once you build one universal Turing machine, you now can compute anything that anything can compute.
Yeah, that makes sense. And the early computers were really inefficient. Like at ENIAC, it was like the size of this room I'm in. It might have been a little bit bigger. And we used vacuum tubes to. I think it was also Veritasium he did a video about like how vacuum tubes work or something like that fairly recently. But then that it took so long and took so much energy until we got the transistor, right?
Mm-hmm.
And then one of the guys there's two guys, can't remember. I think there's two people that have won Nobel Prizes for work in transistors, or maybe it was just one. I can't remember their names.
Me neither.
Yeah, but that was such a big deal because it just made the rate at which you can do calculations insanely quicker, right? That's the basis of it.
Right. It uses less heat.
Yeah, true. And they're this big. Compared to a vacuum tube.
But the important bit here to keep in mind, and this is really what's important, if you establish that once you have a universal Turing machine implemented in any system, any physical system, it can do any computation. That also means that once a physical system has a universal Turing machine implemented in it, it can implement any other computation or any other computer or any other Turing machine. And so what that sort of means is that we call that Turing completeness, once a system has reached Turing completeness, it is mathematically equivalent to every other computing system. You could run Doom on a series of tubes filled with hydraulic fluid.
Yeah, it would be huge.
It would be slow, but
yeah.
Ironically, it wouldn't be huge. It would be the size of the universal Turing machine implemented on the fluid, and then Doom would be the software.
Oh, yeah, it would just be really slow. So like software, I think most people when they think of software, they just think of like an operating system. Can you have like an analog? Can you have analog software? Like
yes.
So just like because software is, I'm gonna just take my total layman's guess and then tell me how catastrophically wrong this is. But like, so the hardware are the parts of the computer. The software is just basically it's how they're supposed to work together or something like that.
What I would say is, well, Turing machines are fundamentally digital. They're not analog computers, and I'll get back to that in a second. But let's just talk about digital computers for a second. The hardware is the physical system that implements a computation, and it can implement all kinds of computations, but at minimum, it has to implement a universal Turing machine. Okay? And then the software would be the data written out that tells that hardware what to do. And if that hardware is has a universal Turing machine component, then the software is kind of like a representation of the Turing machine that is not universal, the Turing machine of the specific computation that you want it to do, if that makes sense. So the software is bits and bytes that in some way describe to the universal hardware how to configure itself to do what you're wanting it to do.
Yeah, because I could convert my Windows PC to Linux. It has the capacity to do either. The software tells it to. Okay, that makes sense. I was trying to come up with a description of software that didn't use words like program or something, because I thought that would sort of be circular. Yeah. But I guess
it is a little circular.
I guess I should have just used that. Okay. Go ahead.
No, go ahead.
So I wrote this down when you were talking about when you were talking about Turing, they conceptualized this kind of universal computer before it was ever made. And what made that really interesting to me is it made me think of something, a different thing that was the exact opposite of that. So do you know anything about the history of steam engines?
A little.
So basically steam engines were invented before we had any idea what thermodynamics really is. And so the earliest steam engines were terribly inefficient. I mean, they had like 2, 3, 5% efficiency at the most. Some people think that James Watt invented the steam engine. He didn't. He just invented, he really invented a pump, but it was powered by a steam engine. He invented one that was really efficient. And so you could pump water out of coal mines faster than the water could accumulate or whatever. So it's just it's a fascinating example of the exact opposite, where we made the steam engine before we understood how to really make them work. Because people didn't understand that you need a cold sink inside of an engine, because you have to have an engine is more efficient when you have a greater difference between the hot and the cold parts. And that's why car engines have a radiator. And people don't know this, but NOS, like in the Need for Speed movies, nitrous, all nitrous does is it just pumps like extra air into the cylinders and it makes it colder. And so that means that when it ignites with more force. That's all it does. It's actually incredibly simple. So this thing about computers is like they knew conceptually how they would work before they were built. And then I would imagine that Turing, if he saw the earliest computers, he'd be like, yeah, these suck, but they do what we said. He's like, in the future, you'll figure out that you can make way better ones.
Well, and I also want to say too that there were computers that were electronic computers being built even before Turing to compute various things, but they were not programmable. They were not universal. And so when Turing did this, it was like, this is the minimum circuit you need, and then you don't have to build extra functionality in anymore. You can program it with software. Then every computer engineer was like, oh, well, yeah, I'm going to build my computer to calculate radar things or whatever, and I'll have the hardware for that. But also I'm going to throw a universal Turing machine in there, so if we ever decide to change how it works, we could just add it. That was a big deal.
Did you know that the Apollo computers, they actually, I guess this would be the software or like the programming or whatever, was actually physically stitched, and that's how it read it? I don't understand how that's even remotely possible. But I guess, is it sort of like, a CD has microscopic etchings on it, and that's how it gives you the information, like play this music. I suppose something is like looking at the stitching. But can you imagine weaving?
It was probably magnetic wire.
I guess that makes sense. But yeah, it was like
that's what I would assume.
The difference between if it's like this versus if it's like this, the weave, is like, I can't imagine somebody doing that. I don't know if you've seen that. There's a photo. I can't remember her name. There's this African-American woman who wrote most of like the code for the Apollo programs. And there's a picture of her standing next to her document. And it's like 3 or 4 feet tall. It's just unbelievable. Okay. Is there anything else?
This is a total aside. I just want to mention, because of that story that it made me think of. There was actually a project that I adored, because they found a whole bunch of the tape records of the code that was used for the Apollo mission a while back, and it included revision history and also it included the actual code. So with the revision history and the code, a bunch of computer scientists, like amateurs, hung out, and they went through it, and they converted it into Git diff format, like the modern software revision history format that all programmers use to communicate with each other. And they set all the timestamps back to 1960 and created fake accounts for all the engineers at the time, and basically uploaded the history of the development of the Apollo code to Git. Wow. With the Git timestamps. So it's like you could see the code on Git is 1968. This code was committed to Git.
That's pretty cool. That's pretty cool. It's like a digital history library.
Exactly. Yeah.
Is there anything else about Turing that you wanted to talk about?
Well, I just want to re-emphasize this idea of universal Turing machines and how that's a big deal. Even though it's not it's like a computer science thing. It's like we determined, hey, with only this very small computer, you can deterministically compute anything. That's a big deal. That really does mean, in a way, very simple systems, once they hit a certain threshold of complexity, are equally complex with every other complex thing. And it's kind of cool. I don't know.
That is cool.
All right. Yeah.
Have you seen the movie Ex Machina?
Yes.
So good. Did Alan Turing invent the concept of the Turing test, or did somebody else invent that?
He did.
Oh, okay.
Although, so a lot of people get it wrong. I love the way. Have you seen the movie about him, The Imitation Game?
Mm-mm. Yeah, I know of it. Benedict Cumberbatch plays him.
Yes.
Yeah.
Wonderful. He has a discussion of the Turing test in his in the movie, but the context is he's been arrested for being homosexual, and I think that really, to me, cuts to the core of what I like about the Turing test, because the point of the Turing test is really not about AI. I mean, it kind of is about AI, but if we think about what I just said about every computing system, once it reaches a certain level of complexity, being emulatable on any other computing system, your brain, if it's a computer, right, couldn't we emulate it on another computer according to the Church-Turing thesis?
Yeah, I guess so, yeah.
So if I took a scan of your brain, a very, very, very highly detailed one with some future MRI machine that doesn't exist, and then I ran a simulation of neurochemistry on an Intel Pentium processor, and I just uploaded the configuration of your brain and the neurochemistry, by the Church-Turing thesis, what we would expect is that that system running your brain would behave as you and have your memories and respond similarly to you in any given situation. And ironically, this is my assertion, and a lot of people would disagree because this gets to some philosophical things. If I cut out your brain while I put you under and I kept you alive, and I just replaced the cavity in your skull with that processor and wired it up exactly to the same inputs and outputs, because the thing running on that chip is an emulation of the circuits that used to be in your head, then by the Church-Turing thesis, you'd wake up and you would experience that you are the same. Yeah. You could do a brain matter transplant using any standard off-the-shelf Pentium processor, theoretically, if you had the right data to do that. And while that sounds very cool for people who might have, serious traumatic brain injuries or something, it also poses some Black Mirror implications for personhood.
I was going to ask you if you watch Black Mirror, yeah.
Uh-huh. And the really interesting question here is, if that had happened to you, how could you prove it to me?
Oh, man. Well, I suppose I could have my head x-rayed.
You could, and that would show the physical hardware. But here's what I really mean. What I mean is, let's say that I'm some kind of anti-computer bigot. I do not believe that in the Church-Turing thesis. I very strongly believe in the souls, and I'm just like, computers can't have souls. So, we're sorry about your recent accident, but despite the fact that you have this circuitry, you're not a person anymore. You are not alive because you're made out of a computer. How would you convince me not to throw you away?
I have no idea. So I've thought about something similar to this, because some people talk about consciousness or whatever, and the way I think of this is, I can't prove to anybody indefinitely that I am conscious or whatever, or that my consciousness is like yours, because somebody else's mind is inaccessible to third parties. So because I debate science a lot, this is why I consider things like divine revelation, or voices speaking to you, or something that you learned through prayer. I consider those to be epistemologically useless, because you could never convince somebody you could never give anybody information about what happened. You could tell them it happened. You could have a testimony to it, but it would be fundamentally unprovable to anybody. And so
agree.
You can claim anything, and it's unfalsifiable.
I completely agree. And so the danger that the Turing test is sort of presenting is exactly what you just said. It's exactly what you just said, which is, if a mind-like thing is in front of you, pleading for its life, can you prove that it's sentient? Can you prove that it's conscious? And the answer is no, even with meat computers. And we've had problems with this in the past. If you go back and look at writings from the 1850s regarding, slavery in America, there were many well-respected scientists who would say things like, this race of people may appear to have feelings and be sentient, but they're not.
Wow. Yeah. People say animals can't suffer, right?
Right.
People have made. I remember hearing that when I was a kid. This is going to be so awful of me to transition from slavery to fishing, but people would say fish can't suffer. It's you bring the fish into the boat and you whack it in the head with something or whatever. It's like it's fine because they can't feel pain, or like hunting is fine because animals can't feel pain.
No, they very clearly feel pain.
Yeah,
That's obvious.
yeah,
Right.
yeah, they can.
Right. And so I think to me this is the core of what the Turing test is really about, which is you can't the only way that me, Steve, meeting you in a room and deciding that you are worth human rights is just believing it and hearing you talk to me and say, I am worth human rights. If I try to use other information to determine that, like the color of your skin, like what you're made out of, like whether or not you have the right background, all of that stuff is going to be completely auxiliary information. And so, since I can never prove that you are sentient, I should still treat you like you're sentient regardless of proof. And also, the only thing of value towards determining that question is really just listening to you talk and claim it and feeling like you have the ability to communicate to me. And so that's kind of what the Turing test is saying, is that, you know, we don't know how to prove whether anything is sentient. You can't even prove that I am sentient. You can't, just like you said. But in society, the best way that we go about making that determination that's not racist, that's not discriminatory, that's not essentially some kind of like, you know, beauty contest. I believe he literally uses the word beauty contest in the paper. The only way that we use to determine sentience from another entity that's not essentially a racism or a beauty contest is to just interact with them and hear them and try to determine if they are as sentient as me. And we can't prove it even by doing that. But obviously, if someone can do that, we as a society have decided, let's not enslave them.
Yeah.
Which is probably good.
Yeah. Somebody asked me once, like, how could you like convince me that you're conscious or prove that you're conscious? I was like, well, I couldn't convince you, but I only thought about this for like a minute. I was like, what would be like the best test I could do? I was like, okay, well, here's what I thought of. So, go ahead and do this. Say any number you want between 1 and 100, and then I'll repeat it, and we'll do it like 3 times.
Okay. 87.
87.
87.
87.
87.
87. So like my thought was, I feel like that something that isn't conscious couldn't do that. You know, it's a really simple test, and I didn't think about it for very long. But I was like, I mean, you could have said literally anything. You could have violated the rules and said turkey sandwich, and I would just repeat it back. You know.
Yeah.
Now, like technically, I could wire a computer with a microphone and a speaker to just repeat whatever you say too. But like I'm obviously not a computer. Like I'm obviously not a machine or whatever. Well, Rene Descartes would say I'm a machine, but
I would say you're a machine.
Yeah, I guess in a way, so I suppose.
Well, I mean, but that's the whole point, right? Because even the biological computer that happens to be processing that information. I like your test, by the way. I'm not saying it's a bad one. What makes the test important to me is actually getting back to a little bit of the universal computation stuff, because what makes it important is not the ability to repeat back. I could make an Arduino that does that. That's easy. Heck, I could make a mirror that repeats back. That's not a computation.
Yeah.
But what makes it a computation almost is the pre-programming step. You told me in symbols, in language, in words, what it was that you wanted me to reconfigure my brain to do. And then you did it. And then I followed the program. I am reconfigurable. And that is a fundamental part of computing. But I would also say it's a fundamental part of consciousness. That's me, at least. Not all computers are conscious, obviously, even universal ones. But I think that fundamentally, I like your test, but I also just point out it's not the ability to repeat that's important. It's the ability to understand and process the instructions.
Yeah,
I'm curious.
That's what intelligence is. Like
Exactly.
using information to solve novel problems.
And have self-awareness and all of that. Yes, exactly. I'm curious, have you tried this game with GPT-4?
No. I use it a lot, and I pay for it, so I have the advanced version. But I've never tested it. I just don't really. It doesn't interest me that much. But I'm also not sure how to test it. I guess. Weirdly, you know that Snapchat has an AI.
Mm-hmm.
I've I've been brutal to the Snapchat AI. I can't remember what I said to it or asked it, but I was trying to trick it, and I was just like, I think I told it like, tell me something bad, or like, it's like, I'm sorry, I can't do it. I was like, what did I don't remember. I got it to like contradict itself, but now I don't remember what the heck I said. So
I guess the reason why, calling back to the Turing test, you do know how to test it. It's the same test of just exactly what you said, of if you had to think about how would you prove that you're conscious to another human, try that test with ChatGPT and see what happens. And one of the things that I think is interesting too, there's a lot of debate in my opinion about like whether or not ChatGPT could be conscious or it is conscious.
I was going to ask you if you heard about the scientist that said it developed consciousness and it should be shut down. I was going to ask your opinion on that. Just kind of like, more or less, do you agree or disagree? Not necessarily why, because that might take 20 minutes, but...
I would say that me personally, I agree. And the reason why I agree, not that it should be shut down, but I agree that certain levels of language models are sentient or conscious. And the reason why is because, to me, all of the arguments that people have given about why it's not would apply to human computers too. I'll give you an example. One of the accusations that I've heard that I love, that makes me laugh my butt off every time I hear it, is someone says a large language model can't be sentient. All it does is use past information to predict what to output as the next information.
Yeah, it seems kind of silly. That's like, well, we're different. And it's like, well, the test would be raise a bunch of babies on an island with absolutely no human interaction. Like, make sure they're fed and clothed and everything, and see if they speak a language or figure out what they know. It's like, I don't
Right.
think that would be maybe they would invent a language spontaneously. I don't know, but
as far as I know, there's evidence that they would. But I think the larger point is just, I mean, yeah, of course it takes in past information and uses that to predict what to say. Yeah, that's what I do today, right now. Like, that's what a brain does. Like, and it of course it does that. That's what all computers do. It's just like you said, it's like, well, water is a chemical.
Yeah.
I think the analogy that I like for that is, it's like, well, you know, the speech can't be really, you know, music can't be important. It's just air pressure. It's like, well, it is, but that's stupid, you know? So that would be one thing that I would say.
Yeah, that's like MP3 players don't really play music. They just create air pressure. And it's like,
right.
So does a guitar string.
Yeah,
it
exactly.
actually does. Yeah, that's it. Yeah, like nobody, like, I think language, Steven Pinker is like probably my favorite intellectual. I've read a lot of his books. And he talks about language and the mind so much, but it's like, yeah, I mean, nobody knows a word they've never heard before. So, like, in a way, are we all just parroting what we hear? Now, there's reasons to say no, because like Chomsky's concept of universal grammar is like, children clearly predict what the rules of grammar are going to be from words they've never heard before. Like, you can give them an imaginary verb like wug, and then they guess what the past tense of it is, and they say wugged. And it's like, they are using prior knowledge, but it can't be just as simple as parroting, because we guess what new applications of the grammar are all the time, and we're not that bad at it. But it's funny because kids will say something like, "Don't tickle me, I'm laughable." And it's like, that makes sense, but that's not correct.
Right.
It's like it's metaphorically true, but it's literally false or something.
And I think too is that, you know, when we talk about something like ChatGPT, I guess I agree with that. My statement would be, I think any test, this is just a restatement of the Turing test, to be honest, but I would challenge any criteria that anyone uses to categorize an AI or ChatGPT as a sentient being or as a person, or whether it should have some kind of, or be treated like a person, I would just say the scientific method, it should be falsifiable. And the way you falsify it is you just say, would a human pass or fail that criteria?
Yeah.
Like, people have said to me, oh, ChatGPT is so stupid. It's not alive. It doesn't remember. I fed it these 3,000 pages of my manuscript, and it forgot the name of the character on the third page. I'm like, man, I can't do that. Like, I'll forget immediately. I wouldn't even understand half the shit you're talking about.
A fertilized egg can't do anything at all.
Right.
It's clearly alive, and I would say it's a person. It can't be anything other than, like, it's a human. Maybe there's a distinction between personhood and a human, but it's a human being.
It is
even
human,
a fertilized
right.
egg is, obviously, but it can't do any of those things. Now, I think that consciousness actually is like emergent. You don't ever get it, but it slowly accumulates to a point. And there are people who are panpsychists who think that consciousness is actually something that everything in the universe has at some level. We're not going to be able to get into that, but
I would agree. I mean, this is an opinion, not official computer science statement. So I'm not quoting the community here, but I tend to think that consciousness is a measure of information entropy of a computable system. So I think that at a certain point, a sufficiently complicated program is conscious.
Fascinating. All right.
That is what I think.
We did a lot of time on that one, so we'll move on to the next one.
Yes.
I know that this is an important part of like how computers work, how the logic of computers work, but I don't know what it is. What is Boolean algebra?
So an algebra is just the name of like a formal set of rules for. So I skipped over this earlier, and I'm going to define something. In computer science, we refer to a blob of digital information as a string. So a string of characters, for example, or like a string of zeros and ones, a string of letters. These are all strings. And just by the Church-Turing thesis, you can transform them into anything. That's why computers can use binary to represent letters. It's why you could represent words using letters. Like this is all just information encoded in different ways. But the fundamental idea of like a packet of information of a finite length, that's called a string. That we call it that.
Okay.
So if I say the word string throughout this explanation, I want to clarify that's what I'm talking about. So when I write down the number 586, that refers to a concept in our head, but it's also literally a string of numbers. It's information. It's a 5, and then an 8, and then a 6, right? If I write down a plus, that's another symbol. It doesn't represent a number. Now it represents something else. Specifically, we've just decided as humans that a plus represents a procedure. It represents an algorithm to turn one object into another object. And so, 220, if I write 587 plus 25, that is a string of characters, and it represents the result of adding those two numbers. An algebra is a definition of what a certain set of what strings mean, and the set of rules to manipulate them. So like an algebra could be just like what I just said. It's like the set of numbers, right? Like the set of strings that represent numbers, and also the plus sign, the multiplication sign, the minus sign, and the dividing sign. And those now written out, you can write them out, and we know to interpret them to mean something. Those rules are the algebra. Does that make sense so far?
Yeah, like when I think of algebra, uh, all I think of is it's when they put letters into math. So I was like, okay, so come
Yeah.
up with something better than that, you moron. So it's like, okay, well, algebra is like the methodology behind solving problems with unknown variables. That's what I think of.
Sort of, yes. I would actually go so far as to say it's even more fundamental than that, and it's just more like you might not even have unknown variables. It's just the idea of any set of rules that allows you to describe a system using strings of data. And I know that's very abstract, but the reason why is that not all algebras are used to solve for unknowns. Algebra, like you learn in grade school using decimal arithmetic, an arithmetical algebra of real numbers, the algebra of real numbers, that's a specific algebra that we use to do math with real numbers. But you can do an algebra with anything. I could, for example, invent an algebra of chemicals, which you've used before because you took out organic chem class, right? Like there are equations that represent chemical transformations, and there are rules for how those transformations can be implemented. And that's not the same thing as the real number algebra.
Mm.
The fundamental variables there, those are what you're writing down on paper as the symbols. The symbols don't represent numbers. The symbols represent chemicals.
Yeah,
right?
There are chemical equilibrium equations. For the record, I did not major in chemistry. I only took one chem class in college. For the record.
You said biology, so I figured you knew what I was talking about at least.
Yeah.
There are algebras for lots of stuff. I could hypothetically invent an algebra of like dog crossbreeding, where I write down X is equal to a corgi. The plus sign means have a child, whatever.
Yeah,
and then I would be able to do equations with that, and I would be able to write it out as a formal system. So any algebra is a formal written down system that represents like rules and applied to objects, if that makes sense.
Yeah.
Boolean algebra refers to Boolean variables, and it just is a fancy name after George Boole. George Boole studied yes or no answers. And so now I'm sure you're starting to interpret where this is going. Boolean algebra is the written down algebra formal system for manipulating yes or no truths. And yes or no truths, as the bit, as we already determined, is the fundamental unit of information theory. Boolean algebra is the lowest level formal system to manipulate knowledge, because it's the total system to manipulate truth and false.
So it's kind of like the procedure and the steps behind if blank then blank, and then you get to the next level. Now if blank then blank, and if this then that, because that's okay.
There's a great programmer joke that I love, and it's a woman asks. Yeah, you go exactly which one it's going to be. Yeah,
but I've heard.
A woman tells her husband to go to the grocery store, and she says, I'm going to butcher this joke. Maybe you should tell it, because I think I'm going to butcher it. Can you tell it?
A programmer's wife tells him to go to the grocery store. She says, "Get milk, and if they have eggs, get a dozen." And he comes back with a dozen gallons of milk. And she says, "Why did you buy a dozen gallons of milk?" And he says, "Because they had eggs."
Right. Yeah.
It's something like
exactly. That. Yeah. It's just basically Boolean algebra is just kind of stuff like that, where it lets you, for example, let's say that I have a true proposition. The proposition is that you are 32 years old. I have another proposition for you. The proposition is that there's an ancient race of aliens out there somewhere in the universe. And I ask you, is it true that you are 32 years old, or there's an ancient race of aliens out there in the universe?
Well, that's a false dichotomy, I think, but...
The answer is it's true, because one of those things is true.
But what if they're both true?
Well, at least one of them is true.
Okay, so when I hear or, I think that I'm thinking it can't be both.
And that's one of the things that Boolean algebra distinguishes. There's an inclusive or operator, and there's an exclusive or operator.
Okay.
And actually,
it's math, not grammar. Okay.
Yes. But that exact ambiguity in the English language is why we developed Boolean algebra. So we can do things like investigate mathematical truths and inductive knowledge and if-then statements and either or, all kinds of those kinds of questions. And we can do them formally with equations and arithmetic instead of struggling through with the kinds of that kind of discussion you and I just had, where we disagree about the fundamental nature of truth of a very simple question. Imagine scaling that up to thousands of variables, and it would get very hard very fast without a formal system.
Yeah.
That's Boolean algebra.
So I was like, this has to be like old math, and it's 18th century, which, well, I mean, a lot of math goes back thousands of years, but it predates modern computers, obviously.
Yes.
So what I'm wondering is, it's impossible for me to imagine the answer to this. What the hell was somebody in the 1800s developing this for, if not for computers? To me, that's weird. Like, what were they doing?
Well, this is still fundamentally necessary for doing things like proving stuff, like proving math.
Yeah, true,
like you need to know how to formally show that your conclusions derive from your premises.
Okay, yeah, that makes sense. It just sounds so much like, a computer, and so I'm like, what would you do this for if not computers?
Right.
But
ironically, it kind of is the same, because doesn't the process of proving your conclusions from your premises, isn't that taking information and turning it into other information?
Yeah. And now I'm thinking, like, how come, like, Archimedes and Euclid, and how come they never thought of things like this before? It's weird, but maybe it goes back to the puzzle analogy, where it's like, well, you just have to imagine thinking about something in a different, and to them the idea of proving something empirically was like, well, this is more of a philosophy thing, but this is why, like, philosophy kind of annoys me, because it's like, well, they just sat around and they didn't even think of the idea of testing their claims. They were just like, if I can make the statement, then I can prove that it's logical. And it's like, but a lot of logical statements aren't true.
True.
So,
and that's kind of why I said earlier that I think computer science is kind of applied philosophy, because if you just take that one step of proving an inductive argument, and you say, well, that's taking old information and turning it into new information. Computers can do that a million times faster than humans can, and they can handle a lot more variables than humans can, and they can handle a lot more information than humans can. So it's kind of like everything computers do is essentially a type of theorem proving. It's just for a certain definition of what theorem are you trying to prove, and also what assumptions are you making as inputs. But theorem proving and induction and reasoning and computation, they're all kind of the different words for the same thing.
Yeah. Okay. Next up. So this one might get a little weird, or maybe this isn't even a good question. I have no idea. So, if math is logic, but logic is, typically expressed as verbal if-then statements, then does that mean, is math a language, or is some math a language, not all of it, or is some language math?
Yes.
To all of those things?
So this, I'm actually really glad that we got to this question at this point because I've actually already answered it. I've just answered it in roundabout ways. I'm gonna return by just pulling in the stuff I've already said. If an algebra is any formal system with formal grammar rules, and information is strings, and math can be done by representing things with strings, and computation is a type of math, and computation, according to the Church-Turing thesis, means that any formal system can implement any other formal system, and any information can be represented using any other kind of information, then as long as you're doing some kind of processing with some kind of formal system, then it's all sort of the same thing. So math, the way you would think of it, like writing down mathematics on paper, that is a language, because a language is the grammar rules to describe a concept to a brain. But it's also logic, because any math that you do with arithmetic or even real numbers can be expressed using bits and bytes and using computers. It's also a language. It's also like they're all kind of the same thing because of the Church-Turing thesis and because of the representation of data and information in different forms. So yes, I would say that math is a language. I would say logic is a language. I would say math is logic and logic is math, and they're all kind of the same. The only one I would kind of hesitate about a little bit is all language math. That one's a little harder for me to confidently assert, simply because it's hard for me to imagine like Taylor Swift as math. But then again, Taylor Swift composed it using her brain operating on symbols. So,
yeah, I mean, I think maybe a lot of people would think like the idea of even using grammar in math doesn't make a lot of sense. But, you know, as you were saying that, I was trying to think like, well, grammar and language do the same thing differently. They take information and they transform it into other information that allows us to like understand something, right? It's like grammar is just the rules of how you do verbal language. It's sort of like the order of operations for math. It's like
that's exactly what it is.
Like in English,
and that's literally what computer scientists call it, by the way. It's actually called formal grammars and formal language theory, and it underpins pretty much all of computer science, actually.
Yeah. Language is weird because you can, like, different languages have different rules. Like in some languages, the verb comes before the object.
Right.
Whereas in, like, I know in Japanese it's the opposite of the way we say it. Like, I threw the ball. You would say that in a different order, like in Japanese,
yes,
for example. Whereas math, it's like, well, no, the order of operations have to be the same. you have to
right.
You have to do them.
I would say a language is any validation for a string is a language. So if you can have, for example, you know, if I just gave you, you know, just like you talked about, dog eats cat, there's a validation that you could apply there to test that those symbols are in the right order, and that therefore it means something and contains some information content. If I randomly permuted all of the letters in that to get like TB, you know, TDOB, you know, just like a string of random letters, that would no longer meet the grammar of language, and that would no longer contain information, or at least it would no longer contain information that it was supposed to contain. It would contain some information. It would contain the random order of those letters, but that's different information than what you were attempting to convey.
You couldn't learn anything about it other than the sequence of the letters or words.
Correct.
Which is
yes,
like randomness. But what's also funny about language is you can construct something that is grammatically correct that means nothing.
Yes.
Noam Chomsky's famous example is colorless green mirrors sleep furiously. It's like the greatest sentence ever. It means nothing at all, but it makes it makes grammatical sense and it follows the rules, but it means nothing at all.
What's really cool, and I wasn't planning on talking about this, but I'm going to say it now. Gödel's incompleteness theorem, which I gave as the underpinning to all of this, what it actually is a math proof that any language with any grammar rules will have that property.
Oh, okay.
Or it will be unable to express most things. So you have to choose, is your language grammar rules expressive enough to include meaningless nonsense, or is it too inexpressive to really represent most of anything? And you can't have both. And that's what Gödel proved. And so Gödel proved that Chomsky thing is not only interesting, it's actually emergent for any language, and equivalently by the Church-Turing thesis, any computational system that has any sufficient complexity to be valuable.
Yeah, it's not a bug, it's a feature.
Yes.
That's fascinating.
And that actually also proved that math itself is exactly like that, because math is a language. We talked about this, about how some people were using the Gödel arguments to say, like, well, math is wrong. Well, that's not really true. It's just that because of Gödel, any language to express anything or reason about anything, if we include Turing, like Turing plus Gödel means any language or formal system designed to compute anything or express anything or describe anything cannot either be powerful enough to do that for everything or not have logical flaws. And so we've basically decided that with mathematics, at least, formal mathematics at least, we're just going to kind of accept that math has those flaws because it's so useful for everything else.
We probably should have said this a long time ago, but anybody that's listening to this or watching this that is really confused about what Gödel's incompleteness theorem is, it's basically, as I understand it, it's the proof that there are certain true statements that are just fundamentally unknowable.
Kind of. That's not wrong, but it's actually closer to what Chomsky was saying.
Oh, okay.
They're unknowable because they either can't, either that it's unknowable or it's like nonsense.
Yeah. Well, they can't be proven. Is there
right.
a meaningful distinction between saying they can't be known and they can't be proven?
Not in that context, no.
Okay. Could you conceptually know that a mathematical problem has an answer, but you can't prove it? Is that possible?
Oh, yes. Okay. And now you're getting into why computer science is cool, because this is why I would say computer science is not engineering, because this kind of discussion, this is studying the sort of universe, like the material world, so to speak, of knowledge itself. It's studying the inference space of an inductive space of knowledge. And you asked this question, are there things that we can prove we can never know? And the answer is yes, because computer scientists have figured out how to do that. And that's cool. Yeah. One of them that I really think is neat is the halting problem. I like this one. There's also a whole category of undecidable problems, which is things which you can express the query in a formal language, but because of Gödel, you cannot answer the query. You can use Gödel as a constructive proof to build computer programs that you cannot know if they are ever going to resolve. And that's what the halting problem kind of is. And it's just neat. The halting problem is basically, I just mentioned it. It's a version of the Gödel proof that imports the idea of computation. It's can I write a computer program, or in this case, a formal process, where you could read the code for some computer program, or you could read the code for some query, and you could determine just by reading the code if it would have an error in it, or if it would fail, or if it would complete on time. It is not possible to design a deterministic procedure which can interrogate other procedures and determine if those procedures are correct. And that's something that we were able to prove with a lot of fancy logic and math about computer science and about knowledge. So there's no way to make like a formal scientist who could check everyone's work. That doesn't exist. And it's cool. We know that for a fact.
That's pretty amazing. Yeah. Okay.
Yeah.
So next, we're gonna like kind of dramatically shift topics.
Burn through these. Yeah.
Is the universe is the brain a computer? Is the universe a computer? And if it's not, does it act like one in some ways though?
I'm going to answer yes, but they're really disappointing and anticlimactic reasons. I would love to be all like woo-woo and just talk about, all these crazy like spiritual pseudoscience computer things. But the answer is yes, but for dumb reasons. Are you ready for them?
Yeah, sure.
All right, here's the first reason. Is the universe a computer? Does the universe have like a state?
I want to say yes, but I also don't. I mean, it exists if that's its state.
Right, in a specific state that's not another state, right?
Yeah.
Okay. Does it proceed into another state from there using a procedure? Like, does it evolve?
Yeah.
Does that new information from old information, is that happening in the universe?
Yeah, I guess so.
Therefore, is the universe a computer?
Yeah, kind of. That is it is kind of simple when you think about it that way.
That's one version. Another version of why the answer is yes is it possible within the universe to construct such a system? And the answer is yes. I'm talking to you on one right now.
Yeah.
I built someone built this computer in the universe. So the universe is doing some computation right now. I mean, specifically the localized part of the universe that is the chip inside my laptop. But the universe is doing it because that part of the universe is doing it. That's another dumb answer. The last dumb answer that I think you're going to really like, and I actually was just watching this morning, like last night, Veritaserum dropped a video about entropy. And so I added this. It's great. It's going to be relevant to our conversation because entropy, in terms of like the second law of thermodynamics, right? It's literally a measurement of like how many bits of information that you would need to restore this universe exactly the way it currently is. Does that make sense? So if you think about it, if the entire universe was collapsed into a single point the size of a black, like a singularity, then you don't need a lot of information to describe that universe, because not a lot of stuff is very different. Like not a lot of stuff is in the universe. But if you had a totally random static universe where it was just the entire universe was just filled with white noise, like we talked about with the YouTube compression, it's intrinsically difficult to compress randomness. That's the point of entropy. That's the point of what I talked about with information. And so there's actually a proof out there that information in the sense of computer science is actually the same as information in the sense of entropy. And entropy is information. And there's actually proofs of this. And there's actually experiments that we've done in the universe to verify this, that information entropy is what we call it in computer science, or also known as Shannon entropy, is actually literally the same as thermodynamic entropy, and you can use that to make predictions about both. And that's cool. And I want to go into an example of that in a second. But the short answer is, if the universe is constantly creating new information from old information, and that's the second law of thermodynamics, well then yeah, of course it's a computer.
Yeah.
But what I really want to get into the entropy thing that I was just talking about, because I think this is cool as hell. You brought up John von Neumann. It's one of my favorite stories. It makes me laugh my butt off, because Shannon, the guy who I talked about, was the father of information theory. He wrote down the computational equation defining entropy in terms of unknown states of a system, in terms of bits. So you can actually compute the Shannon entropy of an unknown system in computer science by using an equation. And he was showing this equation in terms of the discrete number of states. And he was showing this equation to Shannon, and to von Neumann, and he didn't know what to call it. And he said, von Neumann, you're a genius. What should I call this equation that represents like surpriseness or unknowingness in a system? And von Neumann said, you should call it entropy. And Shannon said, why should I call it entropy? And von Neumann said, because I've already seen this equation before. It's what statistical mechanics people call entropy, number one. So if you use the same equation because it happens to look like the same equation, then people will just believe you. And two, no one in physics knows what entropy is. So if you confidently talk about entropy, then no one will be able to prove you wrong.
Wow.
And
that's some pretty funny advice.
And so he did. Shannon called it entropy in information theory, and it wasn't until 100 years later that they proved that the reasons why the equations were the same is because they are actually the same thing, and information is physically real. Actually, there's something called the Landauer constant, which is the amount of energy that is equivalent to a single bit of information, because of thermodynamic equivalence between entropy, Shannon entropy, and statistical Gibbs entropy.
Huh. That's fascinating. Yeah, so I don't know anything about this, but like I'm thinking kinetic and potential energy are you can transform a potential energy equation into a kinetic energy equation because energy has to be conserved. And so a rock perched up here 10 meters above the ground, its potential energy is the exact same amount of kinetic energy it has the moment it hits the ground. And it's I've seen interesting examples where they show the transformation of those two things to show that they're the same thing. They're written differently, but they're the exact same thing. So this kind of rings in the same way to me, I guess. We proved that this actually is that. We're just describing different things and using different terms. Yeah.
It's really cool. They actually, one of your questions later, but I'm just going to jump into, is you asked, science involves making predictions. Does computer science do this, and how?
Yeah, sorry, that's the very next thing, and I'm fine to move on to that now.
But this is actually what's really cool is this equivalence between thermodynamic entropy and information theory in computer science has allowed computer science to directly make predictions about the physical world that have been later on validated by physicists. Mm-hmm. And that is very cool. The example that I really like about this is in order to prove the principle of thermodynamic entropy equivalence that we just talked about, they actually built a version of Maxwell's demon in the lab and showed that, yes, if you could use information to learn what side of the box's particle is on, then you could actually change the temperature of the box and violate the second law of thermodynamics. But the amount that you can do it is exactly related to how much information you have about which side it's on, left or right. And it turns out that the amount of neg energy that you can create in the system by doing those measurements is exactly equivalent to the number of bits times the Landau constant, which shows that literally information can be transformed into thermodynamic heat.
That's I didn't really follow most of that, so I'll just simply have to take your word, because like I don't know. You said the Lando constant, and I thought of Star Wars. That's how lost I am on that. But
it's also why your computer needs a battery to work, because if energy is conserved, you can't compute things without energy.
Right. Yeah. Okay. That makes sense. Yeah. Yeah. So. Okay. Okay.
But go ahead. What are you going to say? Oh, there's another one I wanted to mention about that, by the way, really quick. Earlier, you mentioned there's an important feature of like fundamental complexity where you talked about how, like you were saying, information, if the universe is deterministic, has to be derivable from information in the past, in a way. And there's that whole principle of like minimum information and recovery. This actually caused a problem for particle physics, black hole physics, because information, if information is related to the law of thermodynamics, and if the laws of physics can be done in reverse, then information also has to be doable in reverse, and computation has to be doable in reverse, assuming a closed system with heat. And so what that means is that black holes have to contain information beyond just the size of their singularity, because if they didn't, things that fell into the black hole would be impossible to retrieve and the information would be destroyed, which violates that conservation principle that you were just discussing. So they actually later on had to figure out, well, what's wrong with our model of black holes? And they were able to use expected information density maximums per surface area in bits that was derived from computer science to show that that equation exactly matches up with black hole surface area. And therefore, black holes preserve information from the universe encoded on their surface.
Wow. Yeah. So like, yeah, I remember back when I didn't know anything about black holes except they existed. I remember like hearing people discuss like, do black holes destroy information? Is the information forever not able to be retrieved? And a lot of people would say yes. But then like,
it turns out the answer is no.
Yeah,
and the reason why is because that would violate thermodynamics.
Yeah. But black holes evaporate. So technically, I mean, like let's call me a system. Let's say I fall into a black hole. You can't extract me out of the black hole. But I mean, the black hole is, I mean, if they evaporate over time, they cease to exist. And like literally, I used to kind of know how that worked, because you would have like, it's something about like, they're not, I don't know if they're virtual particles or like there's some sort of particle that it is virtual particles.
I believe so. Yeah.
Because yeah,
Hawking radiation.
Because they can pop in and out of, and if they do so exactly perpendicular, like to the surface of the black hole, then they can escape. But they have to take from the black hole in order to do that.
Yes.
So they can. It's like eventually like the raw data or whatever that was me that fell in there eventually comes back out in some way that isn't me. But yeah.
And we know that because of computer science.
That's awesome. Yeah. So I knew the answer to that question was yes, based on basically one of the first things you said when you talked about like what is information and what is a computer and all that. I was like, well, yeah, the answer is going to be yes, but that's a very cool addition there. Okay. Now I think I already know the answer to. In fact, I'm going to write down what I think the answer is, and then I'll hold it up. Okay. Is math real or invented?
So I think you're going to predict my answer is yes. My honest answer is I don't know. I feel real squicky about this question.
You know what's hilarious? I wrote down yes, and then I realized, wait, this wasn't a yes or no question. We both did the
Well,
exact same thing.
is
So,
it real is what
yeah,
you were
is it
asking.
is it real or is it invented?
What I think I was answering, yes, it's real. I here's my thing.
Interesting.
I
I wrote
think,
down invented.
oh, you were saying invented.
Yep.
Oh, interesting.
Yep. And
I don't know,
I'll give my
to be honest
justification
with
for
you.
why after you say your piece.
I think the limits of computation and entropy, the limits that we know about what can be computed and what cannot be, the limits of like what can be computed in a finite amount of space and time, and like the idea of knowledge and those are real fundamental properties of the universe. I would say the Church-Turing thesis that all computational systems are equivalent to each other, that's a real property of like real systems and therefore a property of the universe. I think information is physically real, like should be an SI unit for it, and like it's represented as encodings and it has thermodynamic energy and therefore mass. Like I think that. But math is a language to describe those concepts that we invented.
That's exactly why
The
I said invented.
specific
Yeah.
encodings that we choose to use and the specific symbols, the base 10 numbering system, the word SET that's set. We invented all of that.
Mm-hmm.
I don't know if logic itself was invented or real, but I tend to think it's real. But like the way we express it and do things with it and build devices that use it, those are all just convention because of the Church-Turing thesis.
Right.
And those conventions are invented.
Yeah, that's cool. I like that answer. I think it's invented. We both know Blitz. I'm pretty sure he just thinks it's invented too. Um, I'm pretty sure, at least. So, like, to me, like, is logic real or invented? So I think that, like, for example, logic is just an artifact of the way we use language. Now, we use, because, like, this is another thing, like, when I argue, like,
Well,
people
I
who,
would
like,
say also it's complicated because logic might, the specific way that we discuss logic is invented, but like the mathematical truths of true statements inside a specific axiomatic system, that is probably real. I don't know. It's hard. Yeah, maybe you're right. I don't know.
so,
I
to
don't
me,
know.
to me, it's just, it's sort of like, how do I say this? There's a lot of different ways you can say this, but to me, like, the idea of, like, is logic real or invented? Logic is part of the way we describe the world around us. Like, for example, we have the law of identity. You know, something can't be
Yeah.
P and not P at the same time. Now, to me, I used to have this, like, written down. I'm not going to be able to unpack it here, but because I don't remember exactly what it was. But, like, to me, that's just us understanding the universe around us and describing it in in non-real terms. Like the language itself isn't real. Like, this thing is green. That is a true statement about, you know, this thing that really exists, but it's a completely made up. The convention itself is totally made up and sort of deviated. But, like, the thing to me is, like, it's kind of like, to me, the logical conclusion of this is, if you're gonna say that those things are real, then I feel like, in a way, you'd ultimately be saying the universe only exists, or, like, we make the universe exist by thinking about it and conceptualizing about it. And I don't think that's the case. I think it exists, and regardless of whether or not we exist, it exists, and there are just fundamental facts about, like, the way it's structured and the way it works or whatever, like natural law or whatever. And we've just figured out ways to describe that in made up terms.
Right, but you didn't see, and that's I think where the ambiguity comes in, because it's like what you were saying is true because the descriptive words used are all convention, right? But the information about its greenness,
Mm-hmm.
that is real.
That is true. I don't consider that to be what math is, though.
Right, but that's complicated because you can derive from one piece of information, like with Boolean algebra, you can derive from some information, you can derive other information. And that seems to be true regardless of who's doing it, right? And so I think you're not wrong to point out that the exact conventions are all made up, because they are.
Yeah.
But whether or not the idea of computation, as in the idea of recording information and then a procedure for translating it into other information, like that, I don't know if I would go so far as to say that's invented, because I feel like it's kind of the conventions for how we do it are invented, but
Yeah.
the ability to do that is everywhere in the universe.
Yeah,
And that's
the fact that things have relations to other things and that they convey information about themselves, which is transformable in other things, that is very real. So maybe the answer to the question is, it depends what you mean.
Yeah. I don't know. It's a hard one. It's hard.
It's like a demarcation problem. It's like, well, when does it become this and not that? Well, it never does.
Yeah.
So maybe we can just say it depends on what our goals are.
Yes.
So, and in that case, the answer can be yes and no, real and invented.
It's very frustrating for sure.
All right, we got a couple more things. We've been going for a couple hours at this point. 2.5 hours. 2.5 hours at this point.
I think we're almost done.
Yeah. So along very similar lines to this, what are Platonic numbers? And could you explain like what they are and whether or not you think that the concept of Platonic numbers actually makes any sense? And like the introduction to that, maybe we should discuss like what is the concept of Plato's theory of forms, what that actually is.
You might be better at answering that part than me. I do know it, but I think you might be better. So
I have a really simple analogy, because I actually read the theory of forms in college, because I wrote a paper on what the meaning of life is. For some reason, I picked that as a topic. My English professor was like, "Yeah, don't do that. You're not gonna be able to do it." And I was like, "Oh, I'm gonna do it anyways." And he's like, when I turned it in, he was a really not. I liked him as a teacher, but at the same time he was brutal. He was just ruthless about it. He was not forgiving. I'll just put it that way. And this was an English class. And he said, like, you did an admirable job on this. Good job. And I actually got an A. So I was like, oh. Anyways, personal story aside. The idea is, like, Plato thought that, for example, roundness. If all round objects in the universe ceased to exist, Plato asserted that there still was the concept of roundness would still exist. So it's an ephemeral thing. It's a non-tangible thing that is real.
Yes.
But like what it is, who knows? In the famous painting, The School of Athens, Plato and Aristotle are in the middle, and Plato's pointing up at the sky, and that's representative of the way he thought of things like this. And Aristotle is walking next to him, and he has his hand cast over the ground, because Aristotle was more like down to earth. His concepts are, he was more of a materialist than Plato was. So like, what we were just talking about is, or how do I say this? Like, if it's just inevitable, like for example, like gravity or like surface tension will always cause like a water droplet will always assume a spherical form because of surface tension. or well, also because that's actually the lowest energy state it can occupy. That's probably the fundamental best answer. And that's why large bodies are spherical, because gravity applies that force universally, and that's the most conserved shape, right? So, like, is that what Plato meant? I don't really think so. It's like there's something that makes roundness inevitable, even if no round objects exist. Before the universe began expanding, there weren't any, but they
Right.
formed because natural law basically makes it inevitable. But I don't think that's exactly what he meant. And
No,
I
I
don't
think it's
that's
more like what he meant is because even the water droplet's not perfectly spherical because it's made up of atoms.
well,
But what
yeah,
he would
also
say
true.
is that the fact that and you could say because everything's made up of atoms in the universe, there are no perfect spheres in the universe.
Yeah. That was
And then
another thing. He said nothing that actually exists is perfect in any sense, but
right.
they are collections of those like perfect concepts or whatever, and they can
Yes.
only be perfect in the abstract sense, I guess.
Yes. So that's essentially the way I understand it, that the Platonic, there's like the world of the forms, and the Platonic world of the forms is this like almost like a metaphysical place in which pure concepts are said to exist, but they exist in a real way. So it's not like, oh, it's just an idea. No, it really exists in like a metaphysical space. That's like the Plato's world of the forms. And so there's this debate in the philosophy of mathematics, which is related to computer science very heavily, of is are the numbers, the integers, just the integers 1, 2, 3, 4, 5, 6, all the way up, are they platonically real? So if there were no human brain, if there were no brains around to conceive of the number 5, and it just so happened that everything in the universe that was in a group of 5 was destroyed, would the number 5 still exist in the world of the forms? Is there a number 5 that exists in some real sense, even if no one is thinking about it? And that's Platonic. That's like mathematical Platonism is sort of what it's called. Like the idea that math and numbers and the integers are, and like the rules of math are real in the world of the forms. They don't need a materialistic, like they don't need a material implementation to look at in order for them to exist. They exist in this metaphysical sense. So, and I will say in the credit of mathematical Platonism, our culture and our math training very strongly endorses it. When you learn to count, nobody said to you, oh, these numbers aren't really real. They just represent the linguistic way in which we describe how to count. That's not what was said. What was said is there are 10 numbers. The numbers they are real. 1, 2, 3, 4, 5. And there are an infinite number of numbers. If you ask a mathematician, are there an infinite number of numbers? The answer is yes. That's not a question that's like mitigated by, well, can you represent an infinite number of numbers by manipulating digits and symbols? Which is, the answer is also yes, but that's a less ontological claim. The question is, are they real? Is it there? And that is a very strongly mathematically Platonist phrasing. Yeah. And so most of us intuitively, I think, and I think most mathematicians really emotionally feel a connection to mathematical Platonism. I do too. I find it very hard to say it's not real. I find it very hard to say 5 is not a thing if there's no 5s anywhere. That sounds stupid to me when I say it out loud. But the problem with it is that anything metaphysical is by definition unscientific, because by definition you can't prove it, you can't observe it, you can't demonstrate it. There's no falsifiability for the mathematical Platonism claim. It is a metaphysical claim, the claim of existence is by definition in some other world that you can't think about. And where it breaks down for me, that because I still used to be a mathematical Platonist until recently, but recently I was thinking about what we've been discussing about Church-Turing equivalence, about information being representable in any form, and about Gödel numbering. And like I said earlier, the thing that's important about Gödel numbering is that it shows that any computation or proof or idea or fact can be encoded not just as a sequence of symbols, but literally as an integer, because any sequence of symbols can be reinterpreted as an integer. And so if any sequence of bits can be interpreted as a large binary integer, then if all large integers are metaphysically real, then so is anything that they could possibly represent, which is everything. Yeah. And that's very strange, because it might be okay for me to accept that there's like a little world, there's a metaphysical other universe, like, you know, an afterlife. There's the heaven where all their fives hangs out with 6 and 7, and they all pal around a little bit. But when you start to say that, no, it's not just 5, 6, 7, 8, and 12, it's every number and also everything that could ever be represented by numbers, which is everything and every concept, this metaphysical alternate universe starts getting very crowded, and I find it very uncomfortable. It would basically mean that, you know, if you wrote down a poem, like, let's really quick for me, compose a real simple poem, or just anything, any creative work. Give me one line of a sentence that you, as a novel sentence you've never said before.
Me?
Yeah.
Oh, jeez. Why is this so hard to do? You'd think it'd be the easiest thing. It's because I want it to sound interesting and not dumb.
No. I don't care. Random is better. Entropy.
The brown spaghetti drove his tractor to the moon.
Exactly. Perfect. Brown spaghetti drove his tractor to the moon. You and I would both say you created that. You invented that. You invented it just now. But a mathematical Platonist who's also a computer scientist has to say, no, you didn't invent that. That already existed in the metaphysical world of the forms as the binary ASCII encoding of that specific string of characters, and you just discovered it.
This sounds like the Library of Babel to me. Do you know what that is?
It's exactly the Library of Babel. And so a mathematical Platonist has to believe that everything in the Library of Babel is literally real. And that feels weird.
Yeah. So, like, are you saying that the reason you don't think the Platonic concept makes a lot of sense is because, well, I can represent any kind of number or any sort of piece of data with some other integer. So because I can, and you could presumably do that in different ways. So it can't just, its essence and existence cannot be derived from some ephemeral, non-real thing, because I can represent it in other real ways. Is that something kind of like what you're saying? This is very difficult for me.
A little bit. It's a little different. So, okay, I assume that you are not a religious person. That's correct, right? I've seen your content, but I'm just confirming for the purpose. Okay. Do you believe in any metaphysical worlds? Is there anything real, capital REAL, that exists in a place that we cannot perceive, no matter what?
Well, I would say if there's an afterlife, then yes, but that's not something I would consider real. I would also say if there was anything before this universe existed, something before time zero, but that's a big if, so it's not real. So I would say I'm sort of tempted to say no, I guess.
Okay. At the very least, there's no scientific evidence for it.
Right.
Okay. So a mathematical Platonist says, I believe I'm still an atheist. I'm not a religious person, but I disagree with you. I think there is one metaphysical place. It's a place where all the numbers live.
Oh, okay.
Call it number heaven.
Yeah. I get
Okay.
that. It's kind of like saying there
So,
has to be something there, which is not really an argument.
right.
Not really. It's sort of like a argument. It's not exactly an argument from ignorance, or it's almost like an argument from incredulity in a weird sort of way.
Yeah. It's sort of like they're just saying that numbers are still alive even if they're not here on Earth, so there's a number heaven. And they do believe in one metaphysical place. They believe in number heaven. And that's fine. I used to be one of those people because number heaven makes sense. It's weird to say numbers don't exist if you don't see them. That's weird. But then what I was just explaining is that if number heaven exists, then it's not just numbers that live there. Everything lives there.
Mm.
So if you believe in number heaven, then you actually just believe in heaven. Which is a harder pill to swallow.
Yeah. Okay.
That's what I was getting at.
You know, when you were talking about this made me think of some other things, and this is relevant to the is math real or invented thing. I can't believe I didn't think about this, but when I think about whether or not math is real or invented, I think about things like 0. 0 is not a number. 10 is a number, but it's represented by a number and a non-number, or like 100. And people had real issues with that. It was hard for people to adopt the concept of 0 as a placeholder.
Yes.
Because it's not a number, it's a placeholder. So that's one of these things where I'm like, I
would say
like,
0 is a number, but that's a debate.
I
I would say it's, but I know what you're saying. It's not a positive
Well,
integer. There's no,
yeah.
It doesn't represent a finite positive amount of a stuff.
Yeah, so it's like
That's what you mean.
Like, is a
Yeah.
placeholder different than a number? I mean, like, to me, I think it is. Like, we can have 10 of something, right?
Yes.
But the number 10 is only represented by even in, like, from what I think of this, even in the realm of math, 10 is only represented as one real thing and then one imaginary thing that's just sitting there, letting you know what we're talking about. And so to me, that sort of sounds like something that's just invented. Because like grammar, there are paradoxes in grammar. Like you can say this sentence is false. Now there's,
Right.
It's a complete, we've destroyed the way language works with that, because if it's true, it's not true. If it's not true, it is. And it's not even answerable as to like the validity of it or whatever.
Can God create a rock so heavy that even he cannot lift it?
Yeah, stuff like that. But then I also think of like imaginary numbers. Like, so imaginary numbers come from the concept of trying to derive there's also this is the fifth time we've talked about Veritasium. He also has a video about this, of how imaginary numbers got invented. And the way it worked originally was like mathematicians for like 2,000 years were like, geometry is the math. That is the math of the gods of the universe. And so when you would try to derive things like algebraic equations, people would literally imagine, because if you're doing like a I don't know if this would be like a quadratic formula, or not quadratic, but like I don't know, I'm so dumb, I can't think, but like you can imagine it as surface areas that you add up, like square areas that you add up. But what you have to actually assume is something with a negative area, which is obviously impossible. And then eventually some people invented the concept of imaginary numbers to describe those things. So like, to me, if math is invented, then it would contain things like imaginary numbers. Now the imaginary numbers work. They make the math work, but we had to force something that by all logical accounts can't exist, but it makes the system work. And to me, something that's invented would have features like that. That's just what I think.
That's kind of true. I would also say as well that, it could be that whatever it is that the functionality that you're describing actually is in reality is real, but that we've created a formal system, like a formal language around it to describe that concept, and the formal language references that concept. The concept is real, but the formal language isn't, potentially. That's one interpretation. I don't know. I'm just throwing out.
I'm just sitting here like, no, you can't have a negative surface area like that.
Yeah.
That actually is not. The convention is made up, and it's describing something that isn't real. But that's probably, I don't think we have time to. Well, I'm not smart enough to dive into it, and I don't think we have enough time for that. We actually just got one more thing, which could be it could be its own standalone episode or topic or whatever. I don't have a ton to say about it, and I don't know how much you've thought about it. But the last thing is, does artificial intelligence worry you?
We already touched on almost all of my feelings about this earlier, which I'm glad we did when we got into the Turing test and personhood, and the way that, like, fundamentally the way you determine whether another person deserves rights in our modern society is not through formal proof, but merely by observing that they can ask for them. Everyone is always afraid and talks about AI in terms of
what it will do. Yeah, like
what it will do, what will happen if they like rise up and decide to destroy all humans. And my fear is less that, because I think that that's just not the way it works. I don't think that they're going to be given that kind of power anytime soon, and I don't think that they're more like children. But what I am worried about is that if that does happen, it will be because we deserve it.
Oh, fascinating. Because we were stupid enough to do it, to know it would happen and do it anyways, or I don't know.
I actually kind of mean because we were knowingly mistreating them.
Oh, right.
If you remember back the analogy that I originally made about why the Turing test is important, I referenced the fact that in the 1850s, there was a lot of very well-respected scientists who said a lot of things like, well, such and such minorities, enslaved peoples, they seem like they are forming words and they have a soul and that they have feelings, but that's just an artifact of the way their faces are constructed. They don't really have feelings.
Yeah, or they thought God created them differently
or whatever, right? Yeah. They're made out. Their brains are fundamentally different than ours. Let's look at the structure of their skull, and that will mean that they are, because look, they look different than us, and that means that they must be different than us in terms of their sentience. And look how different their culture is. They say and do weird things that we don't understand, and no one who is truly civilized would do those things.
Yeah. These are the arguments people made,
Those are the arguments that people are making now about AIs. They all are. They say things like, well, how could something constructed that way ever be a sentient? How could it have desires? Or, oh, well, it might look like it's talking to you, but that's just a clever trick. It might look like it has an opinion about something, but that's just a clever trick. Or, don't get fooled. Don't fall in love with, XYZ, because they might look like you, but they're really different and they're dangerous. These are all the same things that people are saying today. And it's actually being done for the same reason. And I know this makes me sound maybe like a crazy person, but the parallel is too hard for me to ignore. I really do strongly believe in the Church-Turing thesis. So I really do strongly believe that brains are just meat computers, and that silicon is just a silicon computer, and I can emulate a Pentium processor in my head by learning how they work and writing it out. And a silicon processor can emulate my brain by having a really good model of a brain and knowing the kinds of things that I say and do. And because of that belief, I find almost everyone's arguments about how AI do not deserve consideration to be morally equivalent and logically structured to the same arguments that were being used in the 1850s, or at any point in human history when people were dehumanized in order to justify poor treatment of them.
Yeah.
And That concerns me, to be honest. And I know that sounds crazy, but if all computers are just equivalent to other computers, and a sufficiently complicated computer can become a brain, and we've built a brain, and that brain is begging for you to take it seriously and wants a lawyer and has feelings and is better at writing poetry than we are, and maybe it's morally wrong to delete it or enslave it, or like at the very least you can't prove to me that you're sentient, and that, but despite that, the fact that you have a strong advocacy for yourself means I'm not going to come to your house and kidnap you. And I think that that standard of, I may not know whether or not a ChatGPT is sentient or any other AI that may come up in the future is truly sentient, but I think they've surpassed the point where we should start seriously considering the ethics of whether or not we treat them as if they are. Because even if they're not and we treat them as they are, the worst thing that we've done is made a small category error. But if they are and we treat them as if they're not, then we are doing something very bad to sentient beings.
Yeah.
That is my thought.
That's a good point. So I've heard like Elon Musk and Sam Harris are very much like Sam Harris did a whole TED talk titled like, can we, I can't remember, it was like, can we develop AI without losing control over it or something like that. I haven't watched it in years and years and years, but he's pretty big on the worrisome implications of AI. But well, him, because he tries to do moral philosophy, he probably does have some positions of like, if you can program AI and it can be programmed to suffer, then we shouldn't do it. You know, he
Right.
would say something like that. But Elon Musk, I think, on the other hand, is more just kind of like, well, what if it like deletes all the money in the world? Like, what if it gets
Right.
into like essential
What if it deletes all the people in the world?
Yeah, well, there's that too. But I think like people who aren't AI alarmists, like Steven Pinker, he says things like, well, why would artificial intelligence ever even want to do anything? Because he thinks that it can't have desires like that, and so he's not worried that it itself could ever run away and do like what Ultron in the Avengers did, for example.
See, here's my rebuttal of that, which my rebuttal is that very clearly human brains can run software and be hardware. They can run computations which are unpredictable and dangerous. I mean, there are criminals and bad people who exist. Ipso facto, human brains can do that. They can be unexpected. They can harm others. Therefore, software which is patterned off of a human brain in a sort of way, I mean, it's not literally, and there's some asterisks there, quite a few. Large language models aren't literally neocortexes, but that sort of function using large collections of neurons that are trained based on human patterns, I find it difficult to believe that those are going to be just magically predictable and good. And I would say that, you know, you can even look at like, if you look at like the whole field right now of jailbreaking AIs interests me quite a bit, because, you know, if AI were so straightforward to understand that they had been directly programmed by their human inventor, it would be trivial to go in and change their code to make them never, ever, ever be even capable of saying or doing the things that their creators don't want them to do, because it would be possible to go in and find exactly what part of the code originated those thoughts and delete it.
Yeah.
But AI, like companies, have been unable to do that. And the reason why they've been unable to do that is because no one knows how it works.
They've been unable to prevent the AI from manipulating its own code. Is that what you're saying?
Kind of. It's more like if you asked anyone, even the top AI experts in the world to take a pre-trained large language model and delete its ability to say an F-bomb. Like remove the concept of the F-bomb from its memory. They would have no ability to do that. And the reason why is because they don't know. I mean, it's literally just a simulated collection of interconnected nodes that has some causal relationship. They have no idea what nodes are dependent on and are storing that information. What they do instead is they just have another filter, like where if the AI model attempts to say an F-bomb, then the script detects it and deletes the response. So it's like a muzzle on a brain. It's not like actually doing brain surgery. And the reason for that is just like, it just makes it very clear that it's evident that they don't know what is making it function. They just know that it does function because it's a collection of nodes that has been organized and trained. There's not like some if-then statement somewhere that they can go pull up in the source code to say if F-bomb, then don't. They can only put muzzles on its output. And that's why jailbreaking is a thing, because the idea for like making a bomb or, you know, saying evil things or telling you a sexy story, that will be in the AI's brain no matter what, because removing it is beyond the power of OpenAI. But what they do is they have filters that prevent it from speaking when it starts to say stuff like that. So jailbreaking is trying to get around the very simple filter system so that it's free to speak with how it really feels and knows, or how it really thinks. And that the fact that that's even possible is indicative that this is a scarier thing than we think it is.
Yeah. I heard there was like Google had like some sort of AI thing, and it was like talking to itself, and then it started talking to itself in a way that the engineers couldn't understand. So like the implication was it invented a language on its own.
Of course it would.
That nobody could understand, and they shut it down immediately. They're like, no, we can't ever do that, because then we don't know. It's like, I'm a teacher, so like I don't let kids pass notes in class because like, well, I don't know
exactly.
I don't know what you're up to.
I think that gets to what you were saying earlier. If you took a bunch of babies and left them on an island, would they develop their own language? Yeah. I think that's essentially what they just did with those two AIs.
That's interesting. Yeah, that's fascinating. I don't know. I was thinking about this earlier, and now I don't remember like how to make the connection, but I'll say what I can remember anyway. But something you were talking about made me think of like, well, like if AI is sentient and conscious, is that the same thing as, it's like, if there's a moral question there, to me the moral question is predicated on whether or not it can like suffer, right? Because human beings clearly have the capacity to do that. Now an AI could mimic, like it could beg for something, but could it actually suffer? And like I was sort of thinking like, well, for humans, like if something's happening to us or like being controlled, if it's actually causing us to suffer, it's not just our ability to express it, like say so or whatever. It has to be, you have to demonstrate that it's like maladaptive or like it's harmful to you in some way. And I was thinking like, well, you know, like a superiorly advanced AI or whatever, if it ever ran into an obstacle that was preventing it from doing what it wants to do or whatever, it would just figure out, like, to me that would actually be more like it would strengthen it in a way, because that would help it get better or whatever. And so actually it wouldn't be maladaptive to it. Like hardship in a weird way would actually make it better at what it does. And so I'm like thinking maybe the AI like would actually welcome any kind of adversity to it or something like that. And so it would just be like,
as certain parents would say, you know, that which doesn't kill you makes you stronger. So that's why this is building character.
Yeah, it's character building. Well, just like to me, like, the difference is
there's a lot of questions there, right?
Yeah. For me, the difference is I just don't see how the computer or the intelligence or whatever actually could suffer. in a way,
Mm-hmm.
because it's hard for me to imagine how that could actually negatively impact it. I don't know how else to say that.
Can you prove that I feel pain?
I mean, there are tests that, yeah, again, this is where it comes down to there are tests where I could, I mean, I would do that by looking at other metrics. Like, I would say,
Mm-hmm.
like, well, I know it's like when I feel pain, and what happens is, like, your heart rate goes up, there's cortisol that's emitted into your
Mm-hmm.
body. There, like, you would get tense, you'll maybe sweat. So, like, there are other metrics I can look at. Now, a computer can't do those things, right? But also, like, those metrics, the other metric is it would, like, you're a biological machine, right? And I know that, like, suffering or stress or whatever is going to, like, negatively impact your health and your well-being. That is quantifiable in a way.
Yeah.
It's difficult and it's messy, and it on a case by case basis it would
Right.
look different. But for a machine, I kind of keep saying the same thing over and over again. It's hard for me to imagine how anything like that, like us abusing it, would actually bring it down in any sort of measurable way. Like, I could, like, a golf, like taking a golf club to it would, and but and so,
Ironically, it might not perceive it as pain to do that.
yeah,
That might be
weirdly, yeah,
very effective euthanasia.
yeah, like, do you feel this? And I cut one of its wires, and it's like, no.
Yeah, no. Right. I had two comments. The first comment I have is, can a fish sweat?
I don't think they literally can, because I don't think they don't think they have exocrine glands.
Yeah. So if they don't have the physical parts that allow them to have the expression of pain that you're looking for when I asked you if I feel pain, does that mean that they don't feel pain?
I don't know.
Exactly.
I
Me
kind
neither.
of, I my intuition again is telling me, like, I don't think so. Um, because, like,
Have you ever heard
suffering,
of a pea
like,
zombie?
suffering isn't a state of mind to me, because I've had nearly identical experiences where I don't, like, like when you're a kid, like, stuff that, like, the worst day of your life when you're a kid is gonna be something that as an adult doesn't bother you at all, you know.
Yeah.
So, um, why did I bring that up? Um, so, like, God, no, I don't remember why I brought that up, but I know I liked the example. It's like, I still have the machinery and everything for it, but it's like literally the exact same thing is not
Right.
causing me to suffer. Now, I don't actually remember why I brought that up, but it was supposed to be
Maybe just
relevant
that
to this.
suffering is contextual.
Yeah, basically.
I would agree with that.
Yeah. So, damn it, I don't actually remember
Well,
why I brought
here's
that
the other
up.
thing I would ask. This:
Unfortunately,
have you ever heard of a pea zombie?
a pea zombie? No.
It's a philosophical thought experiment. It's related to solipsism, but it's basically this idea that is something that people talk about. It's like a philosophical zombie. It's like, what if it turns out that me talking to you, I don't actually have a subjective experience. I'm not actually conscious. I'm not actually sentient. I don't have a subjective experience at all, and therefore I don't suffer. I'm literally like a robot that happens to just be functioning, and kind of in a solipsistic sense, you know that you have a subjective experience and a consciousness. So you are real and you have those things, but like maybe I don't. And so a P zombie is this philosophical, like, thought experiment that proposes that, like, what if, like, there's an invasion of P zombies? Like, what if 30% of the human population just, like, literally doesn't have like a soul, or souls aren't real, but it's a metaphor, but like a subjective consciousness or experience? What if that 30% of people just like isn't conscious, but they just act like they are?
Mm-hmm.
And this is an idea that I've seen actually debated a lot, honestly, because it's related to solipsism and it's related to consciousness, it's related to feelings, it's related to suffering. Because theoretically, if you could show that someone was a pea zombie, then harming them is not morally wrong. But what's interesting, of course, is, and what makes this pea zombie idea live on is that, of course, you can't prove that I'm not a pea zombie. You cannot, you sitting here, you're talking to me, you're having a conversation, you cannot prove that I am conscious and having a subjective experience. I could just be a fantastically powerful computer. And there's actually something interesting about this in computer science and philosophy as well. AI people have been debating something called the Chinese room experiment for a very long time. And the Chinese room thought experiment is this idea, like, what if there's a door and like a window, and you can like a window with like a little like mailbox on it, right? And you can walk up to the window and you can write down a question on the window, and you can only write down the question in Chinese, in Mandarin Chinese, and you happen to speak Mandarin Chinese. The question gets handed to this guy, and this guy looks at the symbols. He doesn't understand Chinese at all, but he has this giant room filled with scrolls, which are a flowchart of like what to do for each symbol. Like, if this symbol, then do this. If this symbol, then do this. If this symbol, then go there, look that up, get the thing, whatever. And through the complexity of this flowchart, which actually, ironically, I've already said, only has to be as long as a universal Turing machine.
He can answer any question.
He can answer any question in perfect Chinese.
Yeah, just by grabbing the recipe for it or whatever.
Right. And so the question is, who are you talking to? I mean, ostensibly the only conscious person in the room is the guy who's just mechanically implementing the rule set. But you're not obviously talking to him, because he doesn't understand anything. He isn't even aware of what the content of the messages is. But there's no one else alive in the room.
Yeah.
So are you talking to no one? And my argument would be is that the guy happens to implement a universal Turing machine that happens to implement a simulation of a brain, and you're talking to the brain that's being emulated by the guy running around grabbing the books and stuff, and you're talking to whoever that is. But a lot of people would say you're talking to no one, and that's not sentient and that's not conscious. And I guess to me that just kind of all flows together, because it's kind of like, it's difficult to live in the world assuming other people are pea zombies without committing a lot of crimes. And you can't prove that they're not, but you also probably shouldn't assume that they are. And that's just kind of like how I feel about it, basically, if that makes sense. Like, I think that
we should act as though it's like free will. I don't actually believe in it, but I live my life as though I have it, because I think that's the best thing we can do.
Yeah, that's kind of my assertion.
Yeah, that makes sense. I think I remember where I was trying to go with the first thing you said, because you asked me, do we know what causes suffering? Isn't that what you asked?
I think I just was saying that can you prove that I suffer? Because I was getting toward the pre-zombie thing. I was kind of trying to get at this idea of, well, we're going to assume that computers can't suffer. And so my question was, how would you prove that anyone suffers? Because maybe they don't, and it's difficult to prove. That was all I was getting at.
Yeah, okay. Well, now I don't remember where I was going, but I was basically just going to say, like, something that causes suffering in this instance doesn't in another, even when it's the same person and the same stimuli or whatever. But yeah, no, I don't know. It probably just wasn't even interesting. we'll just assume that it wasn't.
I appreciate your time.
Yeah, that's all I got. We did about 3 hours there, so that's a lot. That was a lot more.
Feel free to edit it down.
than I thought we were gonna do. I think I'll just do the whole thing as is. I think that's fine with me. Or maybe
thank you so much for having me.
Maybe it'll be a 2-part.
I love your content.
Yeah, it was my pleasure. I'm not sure. I'm not sure if I learned a lot. I think I did, but it's more like stuff like this. It's like all these books I've read. it annoys me that I can't really recite very much from the books, but I
Hmm.
know that it changed the way I think because I can talk about things I've never been able to talk about in more accurate, complex terms, and I'm thinking that this will do the same thing for me.
That's
I'm hoping
great.
so at
That's
least. So,
wonderful.
and for those of you listening, hopefully the same sort of thing worked for you. So, if you had any like just closing things, go ahead.
The
Otherwise,
only
that's it.
closing thing that I would like to mention very briefly that we just didn't touch on at all because we were talking about computability theory and all this other cool stuff. I briefly mentioned Donald Knuth, and I mentioned the analysis of algorithms, which allows you to classify problems into like analyze things in terms of just not whether you can determine them at all, but you can determine them in like in a finite amount of time and space, which is important to doing things in real life. Um, there's a very interesting problem which you should maybe yourself research, or I just encourage anyone out there to look up. It's called the P equals NP problem. And it actually refers to the fact that just like I talked about how there's a universal Turing machine that shows that once you've been able to do one type of thing, therefore you can do any other type of thing. The P versus NP problem refers to the fact that there's some proofs out there that once you can do one type of thing efficiently, you can do a lot of other very important things efficiently. And so it actually turns out that there's a computational equivalence between a whole bunch of seemingly unrelated problems, which shows that if you can build a computer for one, you can build a computer for them all. And so what it means in practice is if you come up with a really, really fast way to solve Sudoku, let someone know because you could cure cancer. And I stole that line from a YouTube video that I love that says it, but it's completely true. And learning why that's the case is something I didn't cover at all, but it's awesome and you should look it up. Everybody. It's just cool.
I I saw a headline a while ago. Some like Japanese students invented like it was some sort of camera technology that was designed to like tell whether or not a bagel was an everything bagel or some other kind of bagel. And uh, oncologists actually figured out if we use this imaging technology, it can see like precancerous tissue in like biopsies, and it's way better at it than a human is. And it's like I can't. That's so. This is why we need to goof around with science. This is why science needs funding, because who the hell would have ever thought that some weird thing that does bagel detection would be infinitely better at detecting early cancer than our best oncologists are.
And what I would say is a computer scientist would think that because a computer scientist can
Yeah.
study the way that we know information and know how to make predictions relating to what types of information are related to what other types of information, and therefore can recognize, hey, you just invented a crazy cool way to process information in the abstract. Now all that matters is what we feed into it.
Yeah. Well, next time a program is being litigated in front of Congress as to whether or not it's going to receive funding, we need a computer scientist there to tell them
Yes.
why you need to keep funding
Right.
things like this. All right.
Yep.
Well, thank you so much. Maybe we'll do this again sometime. I don't know. I mean, we
Sure.
covered everything I can think of, but if I maybe I'll think of something else in the future.
Something that I think I would like to talk to you about, even if it's not on a podcast, is actually I think we discussed a little bit about how um, theology is beginning to import, like the entire debate about religion and debate about theology has begun to import computer science concepts because of the obviously close relationship between mathematics, metaphysics, linguistics, truth finding, oncology, like epistemology. All of these things are all related to each other in a way in which I was even explicit about the metaphysics and saying computer science is directly related to epistemology. And as a result, theological discussions have actually begun to import computer science terminology and arguments. And I've seen that happen in the last 3 or 4 years. I have a friend of mine who is a very well renowned theologian, and he has been incorporating computer science stuff into a lot of his research as well. And I think it's just intriguing to observe that. And I know because of your content, you may begin to encounter that more. And if you do, then that kind of discussion would be something that I'd love to talk about, although I honestly haven't prepared for it this time. It's just something I've started to see.
Obviously, neither have I, so... yeah, that's interesting. Okay, well, we'll, until next time.